Hello there, and welcome to Science for Sleep, where curiosity gets comfortable, the lights stay low, and we take our time with the parts of the universe that usually refuse to sit still long enough for a proper introduction. Tonight, we're going somewhere very familiar. The Sun. Not a distant galaxy, not a black hole hiding billions of light years away, not some mysterious object discovered at the edge of the observable universe. Just our own star, hanging in the sky every day, bright enough that we have spent thousands of years drawing it, worshipping it, measuring it, photographing it, orbiting instruments around it, and occasionally complaining about it when the weather forecast says 38 degrees. You would think that by now we would have seen nearly everything there is to see. We have satellites watching the sun in ultraviolet light. We have spacecraft measuring particles flowing away from it. We have telescopes studying its magnetic fields. We have probes that have flown closer to the sun than anything humans have ever built. We can watch enormous loops of plasma rise above its surface. We can detect explosions powerful enough to disturb satellites around Earth. We can even measure vibrations moving through the sun and use them to study what is happening deep inside it. And yet, one of the most important regions around the sun has remained frustratingly difficult to observe. Not because it is too far away, because it is too close to something extremely bright. The region is called the inner solar corona, part of the sun's outer atmosphere. It begins just beyond the visible surface and extends outward into space. It is where some of the most important processes affecting the entire solar system begin to unfold. Material there is heated, accelerated, twisted by magnetic fields, and eventually released outward as the solar wind. It is also where scientists want to understand the early development of coronal mass ejections, those enormous clouds of magnetized plasma that can leave the sun and sometimes head toward Earth. We have known the corona exists for a very long time. Seeing it properly is another matter. If you have ever watched a total solar eclipse, either in person or through one of the thousands of photographs people immediately upload afterward, you have seen the basic problem solve itself for a few extraordinary minutes. The moon moves in front of the sun, the bright solar surface disappears, and suddenly, around the black circle where the sun used to be, a pale atmosphere becomes visible. That is the corona. It can stretch outward in delicate structures that were present the entire time, even though moments earlier you could not see them at all. Nothing suddenly switched on. The corona did not appear because the moon arrived. It was already there. The problem was glare. The sun's visible surface is so overwhelmingly bright compared with its surrounding corona that the weaker light is normally drowned out. It is little like trying to see the flame of a candle positioned beside an enormous stadium floodlight, except the difference in brightness is considerably less polite. During a total eclipse, the moon happens to provide an almost perfectly placed natural screen. By blocking the brilliant solar disk while leaving the surrounding space visible, it gives astronomers a rare opportunity to examine regions that are otherwise extremely difficult to study. Unfortunately, the moon has never been particularly interested in accommodating scientific schedules. Total solar eclipses occur only along narrow paths on Earth. They do not last very long. Weather can interfere. Instruments have to be transported to the correct location. Researchers may spend months preparing for an observation only to discover that a cloud has decided it would also like to participate in solar physics. Even under excellent conditions, totality lasts only minutes. Scientists therefore invented coronagraphs, telescopes containing an artificial blocking disk designed to cover the bright sun so that its much fainter surroundings can be observed. It sounds wonderfully straightforward. Put a small disk in front of the sun. Hide the bright part. Look at everything around it. Physics, as usual, noticed that the plan seemed too convenient and introduced diffraction. Light does not behave like a collection of perfectly obedient little arrows. When it passes around an edge, some of it spreads into regions where you would prefer it not to go. In a chronograph, sunlight can diffract around the occulting disk and create stray light inside the instrument. That unwanted light becomes especially troublesome when scientists try to observe very close to the edge of the sun. and unfortunately, very close to the edge of the Sun is exactly where some of the most interesting unanswered questions are waiting. This brings us to an unusual European Space Agency mission called Proba 3. And Proba 3 has taken the basic idea of a coronagraph and done something that, at first, sounds slightly excessive. Instead of putting the blocking disk and the telescope inside the same spacecraft, ESA separated them into two spacecraft, flying through space roughly 150 meters apart. One spacecraft carries the disk that blocks the Sun, the other carries the telescope that observes the corona. When they line themselves up correctly, the first satellite casts its shadow across the second satellite's instrument, effectively creating an artificial solar eclipse in space. ESA's formation operations have brought the pair to about 144 meters separation before the autonomous system takes over and refines their alignment. The spacecraft can then maintain their relative positioning with millimeter-scale precision, which is an impressive sentence until you actually think about what it means. These are not two objects sitting on a laboratory bench. They are satellites. They are moving through space. They are following a highly elliptical orbit around Earth. They are affected by gravity. Their orientation must be controlled. Their positions continually change. Their instruments must remain pointed correctly. Small forces that would normally be almost irrelevant can gradually disturb the formation. And somehow, while all of this is happening, one spacecraft has to place a carefully controlled shadow onto an instrument aboard another spacecraft more than 100 meters away. Then it has to keep that shadow there for hours, without somebody on Earth manually steering the satellites every few seconds. There is something wonderfully strange about the engineering involved. Human beings looked at a total solar eclipse, one of the largest astronomical alignments we can experience from Earth, involving a moon nearly 3,500 kilometers wide and a sun roughly 150 million kilometers away, and apparently decided that the sensible response was to make our own smaller version, using two robotic spacecraft. And it worked. Proba 3 produced its first artificial solar eclipse observations in 2025. Its occulter spacecraft carries a disk about 1.4 meters across. When the satellites are aligned, that disk blocks direct sunlight for the ASPIICS coronagraph aboard the second spacecraft. The telescope aperture remains inside the small shadow cast across it, and the bright solar surface disappears from the instrument's view, while the surrounding corona becomes observable. That alone would make Proba 3 an extraordinary engineering demonstration. But the mission was not designed merely so engineers could congratulate themselves, although after making two independent satellites behave like parts of one enormous instrument, they could probably be forgiven for at least a small amount of congratulation. The separation between the occulter and the telescope changes what scientists can see. A conventional space coronagraph has its occulting disk relatively close to its optical system. Diffracted sunlight limits how close the instrument can look toward the visible edge of the Sun. By moving the blocking disk far away, Proba 3 greatly reduces that difficulty and gives its coronagraph access to a region that has traditionally been difficult to observe continuously from space. ESA describes this as filling an observational gap between what conventional coronagraphs can see and what becomes visible during a natural total solar eclipse. That gap matters because the inner corona is not merely a nice place to take sharper photographs. It contains clues to several problems that solar physicists have been trying to solve for decades. One of them sounds as though somebody must have written the temperatures down in the wrong order. The visible surface of the Sun, the photosphere, has a temperature of roughly 5,500 degrees Celsius. Move outward into the corona, away from the Sun's hot visible surface, and temperatures rise dramatically instead of falling. Parts of the corona reach temperatures of more than 1,000,000 degrees. Imagine standing beside a fireplace, walking away from it, and discovering that the room becomes hundreds of times hotter as you approach the opposite wall. You would probably assume there was another fireplace. Solar physicists have been searching for the equivalent explanation in the corona for a very long time. Magnetic fields clearly play a major role. Waves moving through the Sun's atmosphere may transport energy upward. tiny magnetic reconnection events may release energy. Turbulence may transfer energy from larger structures into smaller scales until it can heat the plasma. There may not be one simple mechanism responsible for everything. The trouble is that some of the action appears to occur in the very region that has been hardest to watch continuously. Then there is the solar wind. The sun is constantly losing material. Charged particles escape its atmosphere and stream outward through the solar system. Eventually that flow reaches Earth, passes our planet, and continues much farther outward. Earth lives inside this enormous solar environment all the time. The solar wind is not something that starts far away from the sun, fully formed and conveniently labelled. It has to be accelerated. Somewhere in the corona, plasma that was part of the sun's atmosphere begins moving outward and reaches speeds of hundreds of kilometers per second. Scientists know a great deal about the solar wind by measuring it farther from the sun. Spacecraft can sample its particles directly. Other solar observatories can watch portions of the corona. What has been much harder is following small structures continuously through the inner corona while that acceleration is beginning. Proba 3 has started doing exactly that. By April 2026, ESA reported that the mission had already produced 57 artificial solar eclipses and accumulated more than 250 hours of high-resolution observations of the corona. Researchers examining those observations were able to track structures moving through the inner corona with unusual detail. Early results indicated that some solar wind structures there were travelling 3 to 4 times faster than earlier measurements had suggested. That is one of those scientific results that sounds modest until you consider the implications. Nobody discovered a new planet. Nobody found an alien radio signal. Nobody opened a portal under Switzerland. Scientists looked at material moving away from the sun and realised that part of the story was happening considerably faster than they thought. For solar physics, that changes the questions you ask. If structures are accelerating earlier or moving faster in the inner corona, then models describing how energy and momentum are transferred through that region have to account for it. If the corona is more dynamic and turbulent than previous observations made it appear, then the apparent smoothness in older data may have been partly a limitation of what we were able to resolve. Sometimes a major scientific instrument does not reveal something completely unknown. It reveals that something familiar has been behaving differently while we were not looking closely enough. Coronal mass ejections create another reason to care. A CME can throw an enormous quantity of magnetized plasma away from the sun. Many travel harmlessly in other directions. Some reach Earth. When their magnetic field interacts strongly with Earth's magnetosphere, the result can include beautiful auroras, but also disturbances affecting satellites, radio communication, navigation systems, and electrical infrastructure. Scientists would very much like to understand these eruptions as early as possible. How do they begin? What happens to their structure while they are still close to the sun? How are they accelerated? How does the surrounding corona influence their movement? What can early observations tell us about what an eruption will become farther out? Once again, the useful information begins in a region that bright sunlight has made awkward to observe. This is why Proba 3 is more than a clever photograph of an artificial eclipse. It is an attempt to turn a rare observing opportunity into something repeatable. A natural total eclipse might give researchers several minutes. Proba 3 was designed to maintain artificial eclipse conditions for hours during suitable portions of its orbit. ESA's mission design allows the satellites to perform these observations near the high point of their orbit, where they are more than 60,000 kilometers above Earth, and the differential gravitational disturbance between the spacecraft is lower, reducing the effort needed to preserve their precise formation. For the telescope, the result is a controlled shadow. For the spacecraft, reaching that point involves a surprisingly elaborate conversation. They use star trackers to determine orientation. GPS information is useful during parts of the orbit. They exchange ranging and navigation data through an inter-satellite link. Cameras on the occulter spacecraft watch lights on the coronagraph spacecraft. A wide-angle visual system helps acquire the target, while a narrow-angle camera refines the relative positioning. A shadow position sensor can determine where the occulter's shadow falls on the coronagraph spacecraft. Small thruster corrections then keep the geometry under control. The satellites are not simply orbiting near each other, they are continuously measuring each other, they are adjusting to each other. For the period when the scientific observation is underway, they behave less like two separate spacecraft and more like pieces of one instrument, whose components happen to be separated by the length of a large passenger aircraft. That last detail is easy to overlook. Astronomical telescopes are usually built around the assumption that their essential optical components are mechanically connected. A mirror stays a known distance from another mirror because both are attached to the same structure. A detector remains aligned because there is metal, carbon fibre, or some other rigid material holding the system together. Probe 3 replaces part of that physical structure with empty space. There is no 144-metre-long beam joining the two satellites. No enormous telescope tube. No rigid frame keeping the occulter exactly where it belongs. The missing structure is replaced by navigation sensors, software, radio links, cameras, and propulsion. Instead of bolting the instrument together, the mission flies it together. That idea may eventually matter well beyond solar science. Future space observatories could use multiple spacecraft to create instruments much larger than any single rocket could launch in one piece. Formation-flying telescopes could separate mirrors, detectors, shades, or other components across distances that would be impractical with a rigid structure. Probe 3 is partly a demonstration of whether that kind of precision can become a normal spacecraft capability rather than an ambitious drawing in an engineering proposal. For tonight, though, our attention stays with the Sun. Because the engineering only becomes interesting scientifically when that little artificial shadow falls in exactly the correct place. Direct sunlight disappears from the coronagraph, the detector looks toward the edge of the Sun, and a region that has spent most of the history of astronomy buried in glare becomes much easier to follow for long periods. Before Probe 3, the best views of that innermost corona often depended on the Moon briefly passing in front of the Sun. Now, two satellites can arrange the geometry themselves. Perhaps you are listening somewhere the Sun has already set. Maybe it is still bright outside. Maybe you are in bed, and the nearest sunlight is currently on the other side of the planet. Wherever you happen to be listening from, it is worth remembering that the Sun does not become quiet when it disappears below your horizon. Its magnetic fields continue shifting. Plasma continues moving. The corona continues heating. The solar wind continues leaving. Eruptions continue forming and expanding whether anyone on Earth happens to be looking upward at that moment or not. So, where are you listening from tonight? And if you happen to know, is the Sun above your horizon right now, or has your part of Earth already turned away from it? It is a slightly different question from asking what time it is, because for most of human history, the position of the Sun was effectively the answer to that question anyway. If you're finding this gentle investigation interesting, or if quietly learning about two satellites manufacturing eclipses turns out to be a surprisingly effective way to end your day, you can leave the video a like and subscribe to Science for Sleep. It helps more people find this little collection of slow science, and it reassures the mysterious machinery behind YouTube that discussions about coronagraph diffraction are, in fact, exactly what everyone has been waiting for. And if you fall asleep before we get very far, that is perfectly acceptable. The satellites will continue flying whether you hear about them or not. What makes their view possible begins with a problem astronomers have faced since long before anyone could launch a spacecraft at all. The difficulty begins with a simple fact that sounds almost too obvious to matter. The Sun is bright. Not merely bright in the way a lamp is bright, or a phone screen at 3 a.m. is bright when you forgot to turn the brightness down. The visible surface of the Sun is roughly 1,000,000 times brighter than the brightest parts of the surrounding corona. Put both of them in the same field of view, and the corona loses badly. Its light is there, arriving at the telescope along with everything else. But the much stronger light from the solar disk overwhelms it. That difference in brightness explains something people noticed long before anyone understood what the corona actually was. During an ordinary day, you look toward the sun, preferably indirectly and with suitable eye protection, and you see a brilliant disk. There is no obvious, enormous atmosphere surrounding it. The sky does not show delicate white streamers extending several solar radii into space. The corona seems absent. Then the moon moves in front of the sun during a total solar eclipse, and almost immediately the situation changes. The bright disk disappears. The surrounding atmosphere becomes visible. For a few minutes, structures that had been hidden by glare can suddenly be studied in considerable detail. The corona may look soft and still in photographs, but it is neither. It is shaped by magnetic fields, filled with plasma, and constantly changing as material moves through it. The important point is that the moon does not make the corona brighter. It makes the sun darker. That distinction is at the heart of the entire problem. Astronomers realized that if nature could reveal the corona by blocking the solar disk, perhaps an instrument could do the same thing. Instead of waiting for the moon to line up perfectly with Earth and the sun, you could place a small opaque disk inside a telescope and manufacture your own eclipse whenever you wanted one. That is the basic idea behind a coronagraph. The modern coronagraph was pioneered in the early 20th century by the French astronomer Bernard Liot. The principle is wonderfully sensible. You point a telescope toward the sun, then use an occulting disk to cover the bright solar surface. Additional optical elements suppress scattered light, allowing the much fainter corona around the blocked sun to emerge. Suddenly you no longer need the moon. You have brought the eclipse inside the telescope. There is only one inconvenience. The moon is much better at the job. A natural total eclipse has an enormous advantage that is easy to overlook. The object blocking the sun is about 384,000 kilometers away from the observer on Earth. The moon is not a little metal disk sitting a few centimeters in front of a camera sensor. It is a huge object at an enormous distance, and that geometry allows it to cover the solar surface while leaving the nearby corona remarkably accessible. Inside a normal coronagraph, the dimensions are much less generous. Your spacecraft cannot conveniently contain a 150-meter telescope tube. The occulting disk has to sit fairly close to the rest of the optical system. In conventional instruments, that distance may be measured in centimeters or tens of centimeters, rather than hundreds of meters. And when an opaque edge is placed close to the telescope, light starts behaving in a way that makes the simple idea of just block the sun considerably more complicated. The culprit is diffraction. We often imagine light travelling in straight lines. For many everyday purposes, that works perfectly well. Put an object in front of a lamp and you get a shadow. Move the object and the shadow moves. If light behaved only like neat little straight-line rays, designing a coronagraph would be relatively easy. But light also behaves as a wave, and waves spread around edges. You can see a rough, everyday version of this behavior with sound. Someone can speak from around a doorway, and you can still hear them even though there is no straight line between their mouth and your ear. Sound waves bend and spread around obstacles. Light does something related, although on much smaller scales because its wavelength is far shorter. When sunlight reaches the edge of an occulting disk, part of the light diffracts around that edge. Instead of producing a perfectly black shadow with an absolutely sharp boundary, the wave nature of light creates patterns and stray illumination in regions that geometrical optics would have predicted should be dark. For most photography, a small amount of diffraction may simply reduce sharpness. For a coronagraph, it is a serious problem. Remember the brightness difference we are dealing with. The corona is extremely faint compared with the solar disk. You do not need a large fraction of sunlight to leak around the occulter before that unwanted light starts competing with the signal you're trying to measure. Even a tiny amount of contamination matters when the thing causing the contamination is about 1,000,000 times brighter than the thing you want to see. It is rather like trying to listen to somebody whisper while standing beside a jet engine. You could reduce the jet engine to 1,000th of its original noise, and still have a fairly poor environment for whisper appreciation. Coronagraph designers therefore have to be aggressive about suppressing stray sunlight. One obvious solution is to make the occulting disk slightly larger. If diffraction creates unwanted light close to the apparent edge of the sun, you can cover a little more than the solar disk. The troublesome region becomes hidden behind the occulter, leaving cleaner observations farther away. And this works. It also creates another problem. The larger the disk becomes, the more of the inner corona it blocks. That means the instrument gets a cleaner view by throwing away the exact region scientists most want to study. This has been one of the central compromises in coronagraph design for decades. You want to block enough sunlight that the faint corona becomes measurable. But you do not want to block so much that the inner corona disappears with it. Reduce the size of the occulter, and you see closer to the sun, but stray light becomes worse. Increase the size and the image becomes cleaner, but the most interesting inner region is hidden. There is no free adjustment knob marked less glare, same view. ESA summarizes the problem directly. Diffraction becomes more troublesome when the occulter is close to the coronagraph, and conventional instruments often respond by using an occulting disk larger than the apparent solar disk. That helps suppress stray light but sacrifices visibility of the inner corona. This observational gap is especially frustrating because the inner corona is not an arbitrary strip of space that scientists would simply like to photograph more clearly. It is where several major pieces of solar physics begin connecting. The visible surface of the sun is called the photosphere. Above it lies the chromosphere, followed by a transition region where conditions change rapidly, and then the corona extends outward for millions of kilometers. If you could watch this region continuously with perfect instruments, you would see plasma controlled and reshaped by magnetic fields. You would see loops, streamers, expanding structures, waves, eruptions, and material gradually being accelerated outward. Some of that material eventually becomes the solar wind. Some can become part of a coronal mass ejection. And somewhere in the same general environment, energy is being transferred in a way that produces one of the oldest uncomfortable facts in solar physics. The corona is much hotter than the visible surface below it. The photosphere is around 5,500 degrees Celsius. The corona routinely reaches temperatures of 1,000,000 degrees or more. Normally, moving away from a hot object is an excellent strategy if your goal is to become cooler. Around the sun, the plasma above the surface apparently did not receive that particular instruction. The explanation involves magnetic energy, rather than ordinary heat simply flowing outward from the photosphere. Scientists have developed several major ideas about how that energy reaches and heats coronal plasma. One involves waves. Movements in the lower solar atmosphere can disturb magnetic fields and launch waves upward. Those waves may carry energy into the corona, where some of that energy is converted into heat. Another involves magnetic reconnection. The sun's magnetic field is constantly being twisted and rearranged by motion in the plasma. Magnetic field lines can change their configuration and release stored energy, sometimes violently. Very small reconnection events occurring frequently across the atmosphere could contribute to coronal heating. Turbulence may also be important. Large-scale motions can transfer energy into progressively smaller structures, eventually reaching scales where the energy can be dissipated as heat. The difficulty is not that scientists have no ideas. They have several good ones. The difficulty is determining how much each process contributes, where it operates, and under what conditions. To answer that, you need observations. And not just occasional still images. You want motion. You want structure. You want to track features over time and see how quickly they move, how they change, how density varies, how magnetic structures interact, and how disturbances propagate away from the solar surface. Natural eclipses are exceptional for showing the inner corona, but they are terrible for continuous monitoring. A total solar eclipse at one location lasts only minutes. The path of totality crosses a limited strip of Earth. Researchers have to put instruments in exactly the right place. Clouds remain stubbornly beyond the authority of solar physicists. Then the eclipse ends, the solar disk returns, and the inner corona vanishes back into the glare. There have been some ingenious attempts to extend eclipse observations. Scientists have flown instruments aboard aircraft to stay within the moon's shadow longer. Teams have positioned observatories across the path of totality so that one station can continue observing after another loses the eclipse. Those methods can increase the useful observing time. They cannot turn totality into a routine event lasting several hours whenever scientists decide they would like another data set. Space coronagraphs solve the scheduling problem. Instruments aboard missions such as SOHO and STEREO have transformed our understanding of the outer corona and coronal mass ejections. They can watch the sun day after day without waiting for the moon. But their occulting systems still have to deal with diffraction. SOHO's coronagraphs, for example, are enormously useful for following material farther from the sun, especially large coronal mass ejections as they expand outward. What they cannot do as effectively is give scientists the same close approach to the solar limb that a natural eclipse provides. ESA notes that existing spacecraft coronagraphs typically lose access to a substantial part of the innermost corona because the occulting disk must hide enough of the field to control stray light. This produces a strange situation in solar astronomy. We can photograph the visible surface of the sun at remarkable resolution. We can observe the outer corona from space. We can send spacecraft directly through the solar wind and measure its particles. Parker Solar Probe has even travelled through the corona itself, yet there is still a narrow observational region close to the edge of the sun, where continuous remote imaging has historically been much harder. In other words, we have been able to study what happens before that region and what happens after it, while part of the connection between them has remained inconveniently difficult to watch. That becomes particularly important when trying to understand how the solar wind accelerates. By the time solar wind particles are measured near Earth, they have already travelled about 150 million kilometres from the Sun. Asking where they were accelerated by studying them only near Earth is a little like meeting runners at the finish line and trying to reconstruct exactly where each one started sprinting. You can learn a great deal from the finish. Their speed tells you something. Their composition tells you something. Their magnetic properties preserve information about where they came from. But watching the early acceleration directly would be considerably more useful. The inner corona contains that early stage. The same problem appears with coronal mass ejections. A mature CME can become enormous. It can expand across millions of kilometres and carry billions of tons of plasma outward. Farther from the sun, coronagraphs can track these eruptions very effectively. But a CME does not suddenly materialise fully grown in the outer corona. Its development begins much closer to the sun. Magnetic structures become unstable. Plasma moves. Loops stretch and reorganise. The eruption accelerates outward. Its shape changes as it interacts with surrounding magnetic fields and solar wind. Those first moments contain information scientists need if they want to understand why one eruption becomes fast and powerful, while another develops more slowly. They also matter for space weather. When a CME is directed toward Earth, forecasters want to estimate its arrival time, speed, magnetic structure, and likely effects. Better physics near the sun can eventually improve the models used farther downstream. The corona, then, presents a slightly irritating scientific arrangement. The easiest parts to observe are not necessarily the parts where the biggest unanswered questions begin, and the part we would especially like to observe happens to sit beside the brightest object available. There is another complication hidden inside the word corona. It is not a solid shell. There is no clean border where the sun ends, the corona begins, and everything can be labelled neatly. The solar atmosphere changes continuously with height. Different structures overlap along our line of sight. Dense streamers can extend far outward. Coronal holes produce different conditions from active regions. Magnetic loops rise above the surface at many scales. When a coronagraph blocks too large an area around the Sun, scientists do not merely lose a decorative inner ring. They lose the lower portions of structures that may extend into regions the instrument can still see. Imagine trying to understand how a tree grows while a wall hides the trunk and the first half of every branch. You can study the upper branches in great detail. You can watch the leaves move. You might even determine which direction the wind is blowing. But understanding how those structures connect to the tree becomes harder, because the most important connection is behind the wall. That is roughly the observational frustration coronagraph designers have spent decades trying to reduce. A natural eclipse lowers the wall dramatically. Conventional space chronographs keep the wall higher because they need protection against diffracted sunlight. This is why eclipse photographs often reveal structures much closer to the visible edge of the sun than routine coronagraph images. It is not because photographers standing in a field have somehow built better solar telescopes than space agencies. They have borrowed the moon, and the moon is an absurdly effective external occulter. Its great distance from the observer means the geometry of the shadow is favourable. The blocking object is nowhere near the telescope's objective. Diffraction still exists, because diffraction always exists, but the arrangement allows astronomers to see remarkably close to the solar limb compared with conventional coronagraph designs. Once engineers understood that geometry was part of the solution, an obvious question appeared. What if the occulting disk could simply be moved farther away from the telescope? Not 10 centimetres, not half a metre, much farther. If the external occulter was separated from the observing optics by a large enough distance, the telescope could sit deeper within a carefully shaped shadow while retaining access to corona close to the solar surface. The unwanted diffracted light would become easier to control. The occulting geometry could more closely imitate the useful feature of a natural eclipse. There would be less need to hide a large section of the inner corona merely to keep the image clean. This is not a new optical principle. Externally occulted coronagraphs have existed before, and engineers have understood for decades that increasing the distance between occulter and telescope could improve performance. The problem was architecture. How far can you move two pieces of the same instrument apart while still calling them one instrument? A metre? 5 metres? 10? Eventually you reach a point where building a rigid spacecraft structure becomes inconvenient, heavy, flexible, difficult to launch, or all four at once. Proba 3's observing distance is roughly 2 orders of magnitude larger than that used in previous coronagraph systems, according to ESA. Its design was created specifically to exploit that large separation, so the instrument could reach much farther into the inner corona while keeping stray light low. One proposed answer would have been to build an enormous boom, place the occulter at one end, place the telescope at the other, launch the entire thing. Then spend the mission hoping your giant space stick remains sufficiently straight. A structure approaching 150 meters would be longer than many commercial airliners. It would have to fit inside a launch system somehow, deploy reliably, maintain alignment, survive temperature changes, avoid vibration problems, and keep the optical geometry stable to extraordinary precision. Nobody looked at that list and became more relaxed. Proba 3 uses a more unusual solution. Remove the structure, keep the distance, let empty space sit between the optical components. The occulter can be on one spacecraft, the coronagraph can be on another. Instead of a rigid beam maintaining their separation, navigation systems and thrusters maintain it. The two spacecraft become, in effect, the ends of a telescope that was never physically built between them. This explains why the approximately 144 to 150 metre separation matters so much. It is not an arbitrary formation flying demonstration with a solar telescope added for entertainment. The science demanded distance. The distance demanded formation flying. And formation flying demanded a level of autonomous control that had not previously been demonstrated this way. The main Proba 3 coronagraph, ASPI-ICS, uses a 1.4 metre occulting disk carried by the occulter spacecraft. The coronagraph spacecraft follows roughly 150 meters away during observations. When the geometry is correct, the occulter blocks direct sunlight before it reaches the telescope and creates a shadow around the observing aperture. ESA's design goal gives ASP-IICS access down to roughly 1.08 solar radii, dramatically closer to the solar edge than the view routinely available to many conventional space chronographs. Even with that large separation, the optical problem does not vanish completely. Some light still diffracts around the external disk. ASP-IICS therefore also contains internal optics designed to suppress the remaining stray light. An internal occulter helps remove light that spills around the edge of the external one. The system is not simply a telescope hiding behind another satellite. It is a carefully designed coronagraph, in which the first major light-blocking element happens to be flying independently 144 meters away, and the alignment tolerance is unforgiving. Move the external disk too far to one side, and direct sunlight begins entering the instrument. Allow the distance or pointing to drift too much, and the carefully designed shadow no longer falls where the telescope expects it. A difference of a few millimeters becomes significant. That sounds almost unreasonable when both spacecraft are travelling through an orbit tens of thousands of kilometers above Earth. A few millimeters on your desk is the width of a small button. A few millimeters between two independent satellites separated by roughly 144 meters is the difference between a useful artificial eclipse and unwanted sunlight washing into an instrument designed to detect something 1,000,000 times fainter than the solar surface. That requirement turns what began as an astronomy problem into a navigation problem. You started with a question about the sun. Why can't we see the inner corona clearly for long periods? Because the solar disk is too bright, so you block the disk. Then diffraction spoils the darkness, so you move the blocker farther away. Then the telescope becomes impossibly long, so you remove the telescope structure and put the blocker on another satellite. Then the satellites have to remain aligned to within millimeters. A solar observation problem has quietly transformed into one of the most demanding formation flying experiments ever attempted, and that is where Proba 3 becomes much stranger than an ordinary observatory, because once the two spacecraft separate and begin operating independently, nothing solid keeps the artificial eclipse together. No beam connects them. No rail holds their distance. No mechanical frame keeps the occulter centered over the telescope. The only thing maintaining the 144-meter-long instrument is a continuous stream of measurements, calculations, camera observations, radio ranging, and tiny corrections made by two spacecraft that have to determine where they are relative to each other, and then behave as though the empty space between them were a perfectly rigid structure. Proba 3 was never designed to hold two satellites motionless in space. There is really no such thing as parking beside Earth and staying there. Both spacecraft are moving continuously along the same orbit, and the trick is to make their motion match so closely that, from their own point of view, they appear almost fixed relative to one another. The mission responsible for this is called Proba 3, and the name tells you something about why ESA was willing to attempt such an unusual arrangement. Proba stands for Project for Onboard Autonomy. ESA has been using the Proba family for years as a way to test technologies that spacecraft may need in the future. Proba 1, launched in 2001, demonstrated that a relatively small satellite could perform tasks such as navigation and pointing with much less intervention from controllers on Earth. Later, Proba missions continued that tradition of putting new technology into orbit and finding out whether it worked when there was no laboratory floor underneath it and no engineer standing beside it with a screwdriver. Proba 3 takes that idea considerably further. Instead of asking one spacecraft to operate more independently, it asks two spacecraft to coordinate with each other so accurately that they can temporarily function as one much larger machine. That is why describing Proba 3 simply as a solar observatory misses half of what makes it interesting. It is a science mission, because it observes the corona. It is also a technology experiment, because the telescope only works properly if the formation flying system performs at a level that had not previously been sustained by two free-flying spacecraft in this way. The science and the engineering are therefore testing each other. If the spacecraft drift too much, the solar observations become worse. If the images are clean and the inner corona becomes visible, that is also evidence that the spacecraft really did maintain the required alignment. The Sun, conveniently, is an unforgiving judge. You cannot persuade it to dim slightly because the navigation system is having a difficult afternoon. ESA built Proba 3 around two spacecraft with very different jobs. The larger of them is called the coronagraph spacecraft. It has a mass of about 340 kilograms and carries the main observing instrument. The smaller one, at roughly 200 kilograms, is the occulter spacecraft. It carries the large circular disc whose job is to block direct sunlight before that light reaches the coronagraph. They are not identical twins. They are closer to two specialists who have agreed to cooperate on one extremely precise task. The coronagraph spacecraft carries the telescope. During observations, it points toward the Sun and looks through an aperture only about 5 centimeters across. The telescope belongs to the instrument called ASPIICS, short for Association of Spacecraft for Polarimetric and Imaging Investigation of the Corona of the Sun. The name is considerably longer than the aperture, but solar missions seem to consider this normal. ASPIICS is a Lyot-style coronagraph, meaning that it uses additional internal optical elements to suppress unwanted sunlight after the external occulter has done most of the blocking. Its scientific purpose is to image the corona much closer to the visible edge of the Sun than conventional space coronagraphs can routinely manage. Its design target reaches inward to roughly 1.08 solar radii. That means the instrument can examine structures beginning only a small distance above the apparent solar surface, instead of losing a large inner region behind an oversized internal blocking disk. The occulter spacecraft has the visually simpler job. It carries a disk about 1.4 meters in diameter. During an observation, that disk faces the Sun and blocks its bright surface. There is no complicated lens inside the disk and no detector recording an image from it. Its primary purpose is to be in exactly the right place, which sounds like a relaxing assignment until you learn how exact the right place has to be. At approximately 150 meters separation, the disk produces a small shadow at the coronagraph spacecraft. ESA describes that shadow as roughly 8 centimeters across, while the coronagraph aperture itself is around 5 centimeters across. This leaves only a modest margin around the telescope opening. If the shadow slides far enough sideways, direct sunlight reaches the instrument and the faint corona disappears beneath the glare again. The occulter, therefore, has to do something the Moon does naturally: stay in front. Of course, the Moon has several advantages. It is enormous. It is moving along an orbit that has been stable for quite some time, and nobody has to refill its nitrogen thrusters. Proba 3 has to reproduce the useful geometry of an eclipse with hardware small enough to launch on a rocket, so the mission depends on control rather than size. Before any of that could happen, both spacecraft first had to leave Earth together. Proba 3 launched on December 5, 2024, aboard an Indian PSL-VXL rocket from the Satish Dhawan Space Center at Sriharikota. The 4-stage launcher carried the two satellites into their highly elliptical operational orbit. They were stacked together during launch rather than flying separately from the beginning, and the combined spacecraft separated from the launch vehicle about 18 minutes after liftoff. The orbit itself was chosen very deliberately. Proba 3 does not circle Earth at roughly constant altitude the way the International Space Station does. Its path is highly elliptical. At the low point, or perigee, the spacecraft come to roughly 600 kilometers above Earth. At the high point, or apogee, they travel beyond 60,000 kilometers altitude. One complete orbit takes about 19 hours and 40 minutes. That long-stretched orbit solves an important engineering problem. Formation flying consumes propellant whenever forces act differently on one spacecraft than on the other. Close to Earth, those differences become harder to ignore. One satellite may experience slightly different gravitational acceleration from the other. There can be traces of atmospheric drag at lower altitude. Other environmental effects can gradually disturb the relative orbit. Every disturbance that pushes the spacecraft away from their desired geometry eventually requires a correction, and every correction uses a little propellant. Propellant is one thing spacecraft cannot conveniently order more of, so Proba 3 performs its most precise formation flying near apogee when the pair are more than 60,000 kilometers above Earth. At that distance, the disturbing effects that try to separate the formation are reduced. This spacecraft can hold their carefully controlled geometry with smaller corrections and therefore use their limited propellant more efficiently. For several hours around this high portion of the orbit, the two satellites can behave like opposite ends of one enormous instrument. Then the formation is deliberately broken. They continue around Earth in a safer relative configuration, pass through the lower portion of the orbit, and later prepare to assemble the virtual telescope again. That phrase, "assemble the telescope," is useful even though nobody attaches anything. Each time the spacecraft acquire their observing formation, they're effectively rebuilding an optical instrument about 150 meters long. A conventional telescope is assembled once on the ground. Proba 3 assembles itself by flying, then it takes itself apart, then it assembles itself again on the next suitable orbit. This repeated separation and acquisition is not an unnecessary complication. Keeping the two spacecraft in their closest, most precise formation throughout the entire orbit would waste propellant and create additional risk. The demanding alignment is only needed during the periods when observations are being made. There is also the small matter that two spacecraft flying close together can collide. Space missions normally treat another satellite approaching within tens or hundreds of meters as something to avoid. Proba 3 deliberately arranges it. ESA has even planned rendezvous and proximity experiments in which the two spacecraft operate at different separations, including distances much closer than the roughly 150 meters used for the main coronagraph observations. The point is not only to study the Sun, but to learn how spacecraft can safely approach, separate, reform, and maintain controlled relative positions in orbit. Those capabilities could become useful for missions that have nothing to do with eclipses. Imagine a large telescope made from several free-flying components, or a spacecraft approaching another satellite for inspection, or a servicing vehicle moving close enough to repair or refuel something already in orbit, or several satellites combining their measurements to behave like an instrument much larger than any one spacecraft. All of those ideas depend on knowing relative position accurately and controlling motion, without turning a sophisticated formation into an expensive collision. There is a practical reason engineers are interested in splitting large instruments into multiple spacecraft. Rockets have size limits. Anything launched into space has to fit within the launch vehicle's payload fairing. Engineers can fold antennas, telescope mirrors, booms, and solar arrays, and deploy them after launch, but increasingly large observatories become increasingly difficult to package. Formation flying offers another option. Instead of launching one giant structure, launch several smaller pieces and let distance between them become part of the instrument. The concept can produce baselines or focal lengths far larger than a rigid structure would allow. The problem has always been precision. It is easy to put two satellites in roughly the same region of space. It is much harder to make them behave like two components bolted to the same optical bench. Previous missions had already demonstrated important parts of formation flying. ESA points to earlier European experience such as Sweden's Prisma mission, which achieved centimetre-level relative control across distances of tens of meters. Spacecraft routinely perform rendezvous and docking operations as well, including approaches to the International Space Station, where accuracy becomes extremely high near the final connection. Proba 3 extends the idea by maintaining millimetre-scale relative positioning between spacecraft that never mechanically attach during the observation. Before Proba 3 could demonstrate any of this though, the two spacecraft spent their first weeks in orbit doing something much less dramatic. They stayed together. Although they had separated from the rocket shortly after launch, the coronagraph and occulta satellites themselves remained physically attached to each other for roughly 6 weeks. Engineers used that period to check their systems while they were still operating as a single stack. Power had to work, communications had to work, attitude control had to work, software had to behave, propulsion systems had to respond correctly, sensors had to be checked. This was not the stage at which anyone wanted to discover that one spacecraft was feeling independent before separation had even occurred. On January 14th, 2025, the pair finally separated from one another while near the high point of their orbit, around 60,000 kilometers above Earth. At the time, they were traveling at roughly 1 kilometer per second around the planet. A carefully controlled mechanism released them, and from then on, Proba 3 truly became two spacecraft. That separation was nearly as important as launch. Once the satellites were free, there was no simple way to put them back together if something went badly wrong. The operations team first had to confirm that the pair were moving apart safely. Then controllers tested the systems that would allow them to determine their relative positions and gradually operate closer together. A safe relative orbit was essential because one of the basic rules of formation flying is that failure should not automatically produce a collision. If communication is lost, or navigation information becomes unreliable, or one spacecraft stops maneuvering, their natural relative trajectories should still provide time for controllers to respond. That is not the sort of detail that appears in the final image of the solar corona, but it is the reason the final image can exist without producing a second image titled "Two Satellites After an Unfortunate Meeting." The spacecraft also have different propulsion responsibilities. The coronagraph spacecraft acts as the formation leader. It carries a monopropellant propulsion system capable of the larger maneuvers needed to acquire and break the formation, manage the orbit, and maintain safe separation. The occulter acts more like the precision follower. It carries cold gas thrusters designed for very small corrections. During the most precise formation flying phases, these thrusters can fire tiny pulses at intervals of about 10 seconds. ESA describes them as operating around the 10 millinewton scale. Rather than making dramatic burns, they repeatedly give the occulter very gentle nudges. A millinewton is not much force. 10 millinewtons is roughly comparable to the weight of about a gram under Earth's gravity. In space, though, a tiny force applied to a relatively small spacecraft, for the correct amount of time, can gradually adjust its motion with remarkable precision. This is why formation flying often looks visually unimpressive. There is no violent steering, no spacecraft swings around sharply and parks beside the other one. The useful corrections can be so small that from a distance nothing appears to happen. Inside the navigation system, meanwhile, everybody's very busy. Both satellites carry reaction wheels, gyroscopes, star trackers, sun sensors, and GPS receivers. The coronagraph spacecraft has its larger maneuvering thrusters, while the occulter includes the additional optical metrology equipment needed to measure its position relative to its partner. Each spacecraft also has solar panels because, rather conveniently for a mission that spends considerable time pointing toward the sun, there is a large energy source directly in front of it. The occulter even carries another scientific instrument called DARA, the Digital Absolute Radiometer. DARA measures total solar irradiance, essentially the total amount of solar energy arriving at the spacecraft. That quantity is important for understanding variations in the sun's energy output and their relevance to Earth's climate system. So while one side of the occulter is busy hiding the sun from ASPIICS, another instrument is carefully measuring how much energy the sun is producing. There is something pleasantly contradictory about that arrangement. One experiment says, "Please block the sun." The other says, "Please measure all of it." Spacecraft engineering is mostly about getting specialists to share a vehicle without arguing. The scientific role of ASPIICS is more complicated than simply producing attractive pictures. It can observe the corona in visible light and through selected spectral bands, allowing scientists to study different properties of coronal plasma. Polarimetric observations help extract information from sunlight scattered by free electrons in the corona. Certain narrow spectral observations can reveal specific ions and plasma structures. What makes these measurements especially valuable is where they're made. Proba 3 is intended to cover the observational territory between ordinary extreme ultraviolet views close to the solar disk and conventional coronagraph views farther outward. That overlap gives researchers a better chance to follow material as it moves from the lower solar atmosphere into the extended corona, rather than watching it disappear from one instrument and reappear later in another. In a sense, the mission exists because solar physicists were missing several pages from the middle of the story. They could read what happened close to the visible sun. They could read what happened farther out. But important events occurring between those regions were difficult to follow continuously. Building an eclipse in space was the engineering answer to that scientific gap, and the basic method has a curious historical precedent. In 1975, during the Apollo-Soyuz test project, the Apollo spacecraft was positioned so that it blocked the sun for observations made from the Soyuz spacecraft. It was an early demonstration of the same broad idea. If one spacecraft can act as an external occulter for another, you can create eclipse-like conditions without waiting for the moon. Proba 3 turns that occasional arrangement into a dedicated autonomous system. That difference matters. Apollo and Soyuz were crewed spacecraft being maneuvered during a historic joint mission. Proba 3 has no astronauts sitting at windows adjusting the alignment. The satellites have to measure and correct the formation themselves. Ground controllers supervise the mission, plan operations, upload commands, monitor health, and can intervene when necessary. But the precision formation itself cannot depend on somebody in Belgium watching a screen and tapping a thruster button every 10 seconds. The communication delay is not the biggest difficulty. Human reaction time and operational workload would already make that approach impractical. The satellites need to know where they are. They need to know where the other spacecraft is. They need to know where the sun is. They need to determine whether the shadow is centered. Then they need to correct any error before that error becomes large enough to spoil the observation. That is where the word autonomy stops being a convenient mission acronym and becomes essential. By March 2025, the mission had demonstrated its first fully autonomous precision formation flight. The two spacecraft flew roughly 150 meters apart for several hours without ground control maintaining the formation. In May, the system successfully created artificial eclipse conditions, leading to the first coronal images released by ESA on June 16, 2025. Consider how strange the geometry is from the spacecraft's point of view. The sun is roughly 150 million kilometers away. The occulter spacecraft is approximately 150 meters in front of the coronagraph spacecraft. The blocking disk is only 1.4 meters wide. Its useful shadow at the other spacecraft is only around 8 centimeters across. Inside that shadow sits a telescope aperture about 5 centimeters wide. And all 4 points involved, the sun, the occulter, the telescope, and the spacecraft's evolving orbit around Earth, must remain sufficiently aligned for the faint inner corona to stay visible. The easiest part is probably the sun. It is large and reasonably easy to locate. The difficult part is making two free-flying machines agree about their relative position, to within a scale comparable to the thickness of a fingernail, while separated by roughly the length of 1.5 football pitches. ESA did not accomplish that with a single magical sensor. Proba 3 narrows the uncertainty in stages. At larger separations, the spacecraft use systems that provide a broad estimate of where the other satellite is. As they approach their observing formation, increasingly precise sensors take over. Star trackers establish orientation by recognizing star patterns. GPS receivers help determine position during the lower parts of the orbit. Radio links between the two spacecraft exchange data and ranging information. A wide-angle camera on the occulter can locate a pattern of lights on the coronagraph spacecraft. A narrow-angle camera then provides more accurate relative positioning. After that, a laser-based metrology system can measure the geometry down to the millimeter level. And finally, the spacecraft can use the shadow itself as part of the navigation process. Around the coronagraph aperture are sensors that measure illumination. If the occulter's shadow is perfectly centered, the light levels around the aperture have the expected balance. If one side becomes brighter than the other, the system knows the shadow has shifted. A correction follows. The solar eclipse is therefore not merely the result of the navigation system, it becomes one of the navigation measurements. The spacecraft create the shadow, inspect the shadow, and use what they learn to keep creating it. That feedback loop is what allows two separate satellites to imitate a rigid structure, even though nothing rigid exists between them. And this is where the mission moves from an unusual telescope design into something that had never been demonstrated at quite this level before. Flying 150 meters apart is easy, compared with knowing that the separation is correct to millimeters. Knowing it is correct once is easier than holding it there for hours. Holding the distance is still not enough, because lateral alignment matters too, and maintaining all of that while pointing the entire imaginary 150-meter instrument toward the Sun requires several independent measuring systems to agree with one another continuously. So now we have met the two machines. One carries the eye, the other carries the disk that allows the eye to see. They were launched together, separated in orbit, and given different propulsion systems because each has a different role in the formation. What remains is the part that makes the whole design possible: how two satellites more than 100 meters apart can repeatedly measure their relative position, correct errors smaller than your fingertip, and keep a tiny shadow sitting on a 5-centimeter telescope opening, while both spacecraft travel through space at orbital speed. Orbital speed makes the whole arrangement sound even less reasonable. Both spacecraft are falling around Earth at thousands of kilometers per hour, yet neither one can simply concentrate on its own orbit. The occulter has to know where the coronagraph is. The coronagraph has to maintain the correct orientation toward the Sun. Their separation has to stay controlled. Their sideways alignment has to remain extremely small. The shadow has to remain centered on an aperture only 5 centimeters across. During the first autonomous formation flying tests, ground controllers initially brought the pair from roughly 600 meters apart to about 144 meters. Once they were close to the desired geometry, control was handed over to the spacecraft themselves. In the fully calibrated observing configuration, the nominal separation is around 150 meters, but that first 144-meter approach is useful because it shows just how the process works. Humans can place the spacecraft near the correct formation. The satellites then have to finish the difficult part on their own. That distinction is essential. If Prober 3 needed constant commands from Earth to maintain every tiny correction, it would not really demonstrate the technology ESA wants for future multi-spacecraft observatories. A formation this precise changes too quickly for ground operators to micromanage it anyway. By the time a controller noticed a small drift, decided what correction was necessary, sent a command and confirmed the result, the satellites might already need another adjustment. So the pair have to close the loop themselves. They observe, they calculate, they correct, then they observe again. This repeats throughout the formation flying period. The process begins with relatively ordinary spacecraft navigation. Each satellite has star trackers. These are cameras designed to recognize patterns of stars and determine which direction the spacecraft is pointing. If you have ever looked at the night sky and tried to identify Orion, you have performed a very crude version of the same task, although the spacecraft is considerably less likely to mistake an aircraft for Betelgeuse. Star trackers give Prober 3 an absolute reference for orientation. That tells each spacecraft how it is rotated in space. But knowing where you are pointing does not automatically tell you exactly where another spacecraft is located 150 meters away. For that, Prober 3 gradually changes from broad navigation methods to increasingly precise ones. During the lower part of the orbit, both spacecraft can use GPS receivers to determine their positions. They also communicate through an inter-satellite radio link, exchanging navigation information and ranging data. These measurements help establish the overall relative geometry. At this stage, being wrong by several meters is manageable. Later, being wrong by several centimeters is not. And eventually, even a centimeter is too much. This is why Proba 3 does not rely on one instrument claiming to know everything. It uses a sequence. As the spacecraft move into formation, a visual navigation system starts looking directly at the other satellite. The occulter carries cameras. The coronagraph carries a pattern of flashing LEDs. The first camera has a relatively wide field of view. Its job is not to perform the final millimeter measurement. Its job is to make sure the other spacecraft is actually where the navigation system expects it to be. Imagine trying to find someone standing at the far end of a dark field. First you want a wide view. Once you spot the person, you can use binoculars. Proba 3 does something similar. The wide-angle camera identifies the LED pattern and gives the spacecraft a relatively coarse estimate of distance, direction, and orientation. Then a narrow-angle camera takes over. Because it sees a smaller region with greater precision, it can refine the relative position to approximately centimetre scale. A centimetre is already impressive. Stand two objects 150 metres apart and try to determine their relative sideways position to within the width of your little finger. Now remove the ground underneath them, put them in orbit, make both objects move. Then ask the measurement to keep working for hours. That would be an excellent achievement for most missions. Proba 3 is still not finished. Once centimetre level navigation has stabilised the formation, the system can use a much finer measurement device called the Fine Lateral and Longitudinal Sensor, or FLLS. This is the laser system. The occulter fires a laser beam toward the coronagraph spacecraft. On the coronagraph is a corner cube retroreflector. A normal mirror sends light away at an angle determined by the direction from which it arrived. A corner cube reflector is designed to return incoming light back toward its source over a useful range of angles. Similar optical devices are used in surveying equipment, and retroreflectors were famously left on the moon by Apollo astronauts, so scientists could measure the Earth-Moon distance by bouncing laser pulses off them. Proba 3 uses the same broad principle across a much shorter distance. The laser travels from the occulter to the coronagraph. The retroreflector sends it back. The occulter detects the returning beam. From that measurement, the spacecraft can determine their relative positioning with millimetre-level accuracy. A millimetre is roughly the thickness of a credit card. The spacecraft are about 150,000 millimetres apart, so the formation control system is trying to regulate the relative position at approximately 1 part in 100,000 across that distance, and the satellites are not connected. That last fact keeps returning because it is the part that makes the entire mission unusual. If you bolt two components to the same rigid optical bench, and their separation changes by a millimetre, engineers can strengthen the structure, improve thermal control, or choose a material that expands less with temperature. Proba 3 has no optical bench running between the spacecraft. There is only vacuum. If the occulter begins drifting sideways, nothing physically pulls it back. Software has to notice. Sensors have to measure the error. The guidance system has to calculate a correction. Thrusters have to produce the right amount of force. Then the spacecraft has to stop correcting before it overshoots. That last part matters. Imagine trying to center a picture frame on a wall. You move it slightly right, too far, back left, too far again. After several attempts, you begin wondering whether the frame was perfectly acceptable where it started. A satellite cannot spend 6 hours oscillating around the correct position, like somebody adjusting a picture frame. Every correction affects motion. In orbit, there is almost no friction to naturally bring that motion to a stop. If a thruster pushes the occulter sideways, the spacecraft continues developing relative velocity until another force changes it. The control system, therefore, has to manage both position and motion. It is not enough to know that the occulter is 3 millimeters too far to one side. The spacecraft also needs to know whether it is already moving toward the correct position, how quickly that movement is happening, and how much thrust will fix the error without creating a new one. This is guidance, navigation, and control working as one system. Navigation answers, "Where are we?" Guidance answers, "Where should we be?" Control answers, "What do we fire to get there?" Prober 3 has to repeat those questions continuously. For the finest adjustments, the occulter uses cold gas thrusters, operating at around the 10 millinewton scale. 10 millinewtons is a very small force. On Earth, it corresponds roughly to the weight of a 1-gram object. You could hold something producing that much force on your fingertip, and probably wonder whether it was doing anything. On a spacecraft in nearly frictionless orbital motion, tiny forces are exactly what you want when the required correction may be measured in millimeters. ESA designed these thrusters so the occulter could make gentle repeated adjustments instead of giving itself an enthusiastic shove and immediately ruining the eclipse. The coronagraph spacecraft has a different propulsion system, using larger, roughly 1 Newton scale maneuvers for tasks such as orbit control, formation acquisition, and collision avoidance. The two propulsion systems reflect the different jobs of the satellites. The coronagraph establishes the broader motion of the pair. The occulter performs much of the fine relative adjustment required to keep the shadow aligned. You can think of one as positioning the table and the other as adjusting the microscope, except the table is moving around Earth. After the laser system brings the relative position to millimeter accuracy, there is still one final measurement that matters more directly than any of the others: the shadow itself. Around the coronagraph's 5 cm aperture are photodetectors forming what ESA calls the shadow positioning sensor. The idea is beautifully simple. If the occulter is perfectly aligned with the Sun and the coronagraph, its shadow falls symmetrically around the telescope aperture. The sensors around that aperture should therefore receive the expected balanced illumination. If the shadow shifts sideways, one side becomes brighter than the opposite side. The spacecraft can detect that imbalance. Then the formation control algorithm can command a correction. At this point, the spacecraft are no longer merely calculating whether the geometry should produce an eclipse. They are measuring whether the eclipse is actually where it belongs. That is an important difference. GPS can tell them their orbital positions. Cameras can tell them where the other spacecraft appears to be. A laser can tell them their relative separation and lateral alignment with extraordinary precision. But the scientific requirement is not ultimately keep two satellites 150 meters apart. The requirement is keep the coronagraph inside the occulter's shadow. The shadow positioning sensor measures exactly that, and the shadow is not generous. ESA describes the occulter as producing an approximately 8 centimeter wide shadow at the coronagraph spacecraft. The telescope aperture is about 5 centimeters across. Subtract one from the other and you begin to see why millimeters matter. There is only about 3 centimeters of difference between the diameter of the useful shadow and the diameter of the opening that must remain inside it. If everything were perfectly centered, that would leave roughly 1.5 centimeters of margin around the aperture. That is not much room for a formation extending across 150 meters. For comparison, imagine standing at one end of a 150-meter corridor with a laser pointer and trying to keep its beam inside a circle only a few centimeters wide at the other end. Then imagine that the wall containing the circle is also moving. Now imagine you are moving too. Then remove the corridor. That is closer to the Prober 3 problem. The satellites are also aligning along the direction of the Sun, which introduces another accuracy requirement: pointing. A formation can have the correct separation and still fail if the line connecting the spacecraft is not pointed correctly toward the Sun. ESA's target includes very fine angular alignment down to arcsecond scales. An arcsecond is 1/3600th of a degree. Human eyesight cannot resolve anything close to that. From the ground, Earth's atmosphere often causes stars to wobble by amounts comparable to an arcsecond or more. Prober 3 is trying to hold the orientation of a virtual 150-meter-long instrument to that sort of angular scale, while the two ends are physically independent. This explains why the system needs several kinds of sensors rather than simply installing a better camera. Each sensor is good at a different part of the problem. Star trackers know orientation against the sky. GPS gives broad position information when available. Radio links help establish relative distance and allow the spacecraft to exchange navigation data. Wide-angle vision finds the partner spacecraft. Narrow-angle vision improves the estimate. Laser metrology pushes the measurement into the millimeter range. The shadow sensors confirm that the solar alignment itself is correct. The navigation software combines these measurements into one estimate of the formation. That process is called sensor fusion, and it solves a problem that appears in many autonomous systems. No sensor is perfect. A camera can be affected by lighting. A laser can have its own calibration errors. Star trackers have noise. Radio ranging has limits. Measurements arrive at different rates and with different uncertainties. Rather than believing one instrument absolutely, the navigation system uses all of them to build the most reliable estimate possible. Your own brain does something similar. If you stand in a moving train, your eyes tell you about your surroundings, your inner ear senses acceleration. Pressure in your feet tells you how your weight is shifting, and your muscles report their position. When those systems agree, standing is easy. When they disagree, you may discover why trains contain handrails. Proba 3 has the spacecraft equivalent of several senses, and its control software has to decide what all of them mean together. Before launch, ESA engineers tested these systems on the ground in some unusual ways. The vision-based navigation equipment needed long distances to operate realistically, so test versions of the cameras were taken into a long corridor at ESA's ESTEC Technical Center in the Netherlands. Lights were reduced, obstacles moved, and LED targets were placed far away so the cameras could practice recognizing the same type of pattern they would later see in orbit. Later tests brought flight hardware together in clean rooms, where cameras, LEDs, laser equipment, and shadow sensors were operated in sequence. This was harder than it sounds because the real spacecraft were designed to work about 150 meters apart, and clean rooms are rarely built with a spare 150-meter empty optical path waiting for 2 experimental satellites. Engineers therefore had to simulate pieces of the geometry. At one point, a robot held the laser retroreflector so the navigation hardware could be tested, even though the real spacecraft could not be placed at their operational distance. Testing spaceflight hardware occasionally requires very advanced robotics. It also occasionally requires finding a sufficiently long hallway. Orbit removed those limitations. In March 2025, the first major formation flying test began with ground-commanded maneuvers. The spacecraft were initially around 600 meters apart. Controllers used GPS-derived information and thruster commands to reduce that distance to about 144 meters, while also moving the satellites toward the correct sun-pointing alignment. Then autonomy was activated. The narrow-angle camera detected the coronagraph spacecraft. The onboard navigation converged on a solution. The occulter began controlling its own relative motion. From that point, engineers on the ground were watching rather than steering every adjustment. The occulter then had to move laterally by roughly 50 meters, so that its shadow reached the correct area on the coronagraph spacecraft. That is worth visualizing. The satellites were already flying close to their desired distance. But being the correct distance apart is not the same as being directly lined up with the sun. The occulter had to slide across relative to its partner until the coronagraph entered the shadow. Once there, the system maintained the formation for hours. Afterward, the satellites deliberately broke formation before heading toward the lower portion of their orbit. Then, when they returned toward apogee on the next orbit, they had to find each other and build the formation again. And they did. That reacquisition is almost as important as maintaining formation in the first place. A spacecraft that can hold a position after engineers carefully place it there is useful. A spacecraft that can repeatedly approach, identify its partner, refine its relative position, enter precision formation, complete an observation, safely separate, and then perform the entire sequence again is much more useful. That is what makes Proba 3 relevant to future missions. The goal is not one perfect eclipse. The goal is a repeatable capability. By May 2025, after further calibration and testing, ESA announced that the pair had achieved millimetre precision formation flying for several hours without control from the ground. The fine lateral and longitudinal sensor had been integrated into the autonomous control loop, and the shadow positioning sensor was being used successfully to keep the coronagraph in the correct shadow geometry. ESA described the resulting formation as stable beyond expectations. This was not simply an engineering milestone that happened to involve the Sun. It changed what kind of telescope could exist. Think again about the physical size of the instrument. The occulter is on one spacecraft. The detector and coronagraph optics are on the other. About 150 meters of nothing sits between them. Yet optically, that empty distance is part of the instrument. If an engineer tried to build an equivalent rigid structure, it would be longer than the wingspan of a Boeing 747 and much longer than the James Webb Space Telescope is wide after deployment. Launching such a rigid telescope would be extremely difficult. Keeping it straight to millimetre precision while one side is illuminated by the sun and temperatures change across the structure would create another collection of problems. Proba 3 avoids the giant beam completely, navigation replaces metal, software replaces structural stiffness, thrusters replace adjustment screws. This does not make the engineering easier. It changes which engineering problem has to be solved. The reward is scale. Once two spacecraft can behave like a single instrument across 150 meters, the same principle can be imagined across greater distances. Future telescopes might use separated mirrors. Several spacecraft might combine signals to create extremely long interferometric baselines. A large starshade could fly tens of thousands of kilometers in front of a telescope to block the light of a distant star while the telescope searches for faint planets beside it. Other formations could perform Earth observation, gravitational measurements, or astronomy that is impossible with one conventional satellite. Proba 3 does not prove that every one of those future concepts will work. It proves something more basic that all of them need. Two independent spacecraft can be made to act as though the space between them is part of a controlled machine. There is one practical limitation, and it explains why Proba 3 cannot simply maintain this perfect alignment indefinitely: propellant. The spacecraft are constantly being disturbed by forces that do not act identically on both of them. Earth's gravity is slightly different at each satellite's position. At lower altitude, traces of atmosphere produce drag. Solar radiation pressure can affect them. Small differences in spacecraft mass, orientation, and surface area matter when your allowed drift is measured in millimeters. Every time the formation control system cancels one of those disturbances, it spends a little propellant. This is why the artificial eclipses occur near apogee, when the spacecraft are more than 50,000 to 60,000 kilometers above Earth. Far from the planet, the difference in Earth's gravitational pull between the two spacecraft becomes smaller. Atmospheric drag is essentially gone. The environment is quieter from the perspective of relative navigation. That allows the pair to maintain formation with less fuel. For up to roughly 6 hours during a suitable orbit, Proba 3 can hold the geometry needed for eclipse observations. Then the formation is broken. The spacecraft pass through perigee separately. Later, as they climb outward again, they rebuild the virtual telescope. Their full orbit takes about 19 hours and 36 minutes. So the rhythm of the mission is not continuous formation flying. It is repeated precision, approach, acquire, align, observe, separate, orbit, return, and do it again. Each time, the occulter eventually has to place that 8 centimeter shadow over the 5 centimeter aperture. Each time, cameras and lasers have to agree. Each time, the onboard software has to decide which tiny correction is necessary. Each time, the cold gas system has to make that correction without creating a larger problem. There's a useful contrast here with a natural eclipse. During a total solar eclipse on Earth, nobody controls the moon. Nobody measures its position every 10 seconds and gives it a corrective push. Its orbit provides the alignment, and the shadow crosses Earth whether astronomers are prepared or not. Proba 3 reverses that arrangement. The astronomers do not travel to the shadow. They move the shadow to the telescope. And because the shadow can be held there for hours rather than minutes, the scientific instrument can do something natural eclipses rarely allow. It can watch the corona change. A photograph can reveal structure, a sequence reveals motion, a long sequence can reveal acceleration. That difference becomes crucial when small features are moving rapidly through the inner corona. During the first artificial eclipses, the spacecraft had finally solved the geometrical problem that had limited coronagraphs for decades. The bright solar disk was blocked outside the telescope. Diffraction was reduced. The inner corona came into view. The formation stayed locked long enough to record not just a brief glimpse but sustained sequences of observations. The first useful images looked almost ordinary at first glance. There was a dark circle where the sun should have been, and around it was a faint halo of light broken into thin structures, some stretched outward in long narrow rays. Others curved around the hidden solar disk. Brighter regions appeared near the edge, while fainter material extended farther into the field of view. If you had seen the image without knowing how it was made, you might have assumed somebody had photographed a natural total solar eclipse from Earth. That was exactly what made it important. There was no moon in front of the sun. There was no expedition standing beneath a narrow path of totality. There was no race against 2 or 3 minutes of darkness. The black disk in the middle of the image had been produced by one spacecraft, flying about 150 meters in front of another spacecraft, and the corona surrounding it had been recorded after the pair maintained their alignment to millimeter precision. For solar physicists, the most interesting part was not simply that Proba 3 had managed to photograph the corona. Spacecraft have been photographing the corona for decades. It was where the new instrument could look. ASPIICS was designed to observe down to about 70,000 kilometers above the visible solar surface, roughly 1/10 of the Sun's radius. That places its inner field of view much closer to the solar limb than operational space coronagraphs, such as SOHO's LASCO C2 or Solar Orbiter's METI can normally reach. ESA describes this as the long missing observational region between instruments that examine the solar disk and low atmosphere, and conventional coronagraphs that begin farther outward. 70,000 kilometers may not sound especially close. If you drove that distance on Earth, assuming you could somehow keep going without encountering oceans, borders, or a growing suspicion that you should have taken a flight, you could circle our planet almost twice. Around the Sun, 70,000 kilometers is close enough to place an instrument inside a part of the corona that has historically been difficult to monitor in visible light for long periods. This is the region where structures are still strongly connected to the magnetic environment near the Sun. It is where streamers begin taking shape. It is where prominences can rise and erupt. It is where plasma starts moving outward into the extended corona. And it is where many processes that later become obvious farther from the Sun are still developing. The first public Proba 3 coronal images were released by ESA on June 16, 2025. Some of the observations had been made on May 23rd, after the spacecraft had successfully demonstrated the precision formation required to manufacture their artificial eclipse. ESA reported that the first images already showed the inner corona with very low levels of stray light, which was the result the entire 2 spacecraft design had been built to achieve. Low stray light may not sound like the most dramatic scientific achievement. There are no explosions in the phrase. But for a coronagraph, low stray light is the difference between seeing the corona and seeing a bright optical mess created by the sun you were trying to hide. A SPIICS does not simply produce one ordinary photograph and call the observation complete. A full coronal image can be assembled from 3 exposures of different lengths. Shorter exposures prevent the brighter inner regions from becoming overexposed. Longer exposures collect enough light to reveal fainter structures farther out. The images are then combined so that the final result contains useful detail across a much wider range of brightness. ESA's ASPIICS team used this method during the early observations to produce a complete view from the occulted sun toward the outer edge of the instrument's field. The reason this is necessary is similar to trying to photograph a dimly lit room containing a very bright window. Expose the camera for the room, and the window becomes a featureless white rectangle. Expose for the window and the room becomes dark. Modern cameras solve versions of this problem by combining exposures, and the coronagraph uses the same basic idea on a rather less cooperative subject. Except in this case, the bright window is the solar atmosphere near a star with a diameter of nearly 1.4 million kilometers. ASPI-ICS can also examine the corona in several different ways. One observation mode records visible light scattered by electrons in the corona. Sunlight leaves the photosphere and travels outward. Some of that light encounters free electrons in the hot coronal plasma and scatters toward the telescope. By measuring this faint scattered light, scientists can trace the distribution of material around the Sun. The instrument can also measure polarized light. Light is an electromagnetic wave, and polarization describes the orientation of those waves. Scattered coronal light has a different polarization signature from some of the unwanted background light produced by interplanetary dust. By measuring polarization, researchers can separate components of the image and obtain cleaner information about the electron corona. One of the first Proba 3 images released in June 2025 used this technique, revealing the inner corona in polarized white light. That may sound like a complicated method for producing a photograph that still looks like a fuzzy ring around a black circle, but the apparent fuzziness contains structure. In processed ASPIICS images, the corona breaks into numerous thin, hair-like features. Those features are not solid strands. The corona is plasma, a gas heated enough that electrons are separated from atoms. Its particles respond strongly to magnetic fields, and those magnetic fields organize the plasma into structures that can remain coherent across enormous distances. The result is that the corona often gives scientists a visible map of invisible magnetism. Where magnetic field lines form large closed loops, plasma can become concentrated along them. Where fields extend outward, material can escape more easily. Where different magnetic regions interact, the structure can change suddenly. A photograph of the corona is therefore not just a photograph of glowing gas. It contains information about the magnetic architecture controlling that gas. One of the first ASPIICS images made this especially clear. On May 23, 2025, the instrument observed the corona through a spectral filter associated with highly ionized iron. The resulting view highlighted extremely hot material, reaching temperatures around 2 million degrees Celsius. In the upper left portion of the image, scientists could see a hot loop extending away from the solar surface, the type of structure that can appear following a solar flare. This is one reason ASPIICS uses more than ordinary white light imaging. Different wavelengths tell different stories. A broad visible light image is especially useful for following electrons and large-scale structure. A narrow spectral filter can emphasize plasma containing particular ions. Another filter can reveal cooler material that would otherwise be difficult to separate from its surroundings. You are looking at the same corona each time. You are simply asking different parts of it to identify themselves. An early observation made on March 25, 2025 demonstrated this with a prominence. Prominences are structures of comparatively cool, dense plasma suspended above the solar surface by magnetic fields. Cool requires some clarification when discussing the Sun. The prominence observed by ASPIICS contained material around 10,000 degrees Celsius. That would be an inconvenient temperature for almost anything in your kitchen. Inside a corona exceeding 1 million degrees, however, 10,000 degrees counts as remarkably cool. SPIICS observed the structure using a spectral line associated with helium. In that image, a cloud of the cooler plasma was visible near the edge of the occulting disk. The observation was especially interesting because the instrument had been deliberately pointed slightly away from its ideal alignment, bringing the hidden solar disk unusually close to the occulter's edge. Even under that configuration, the coronagraph was still able to recover detailed structure in the nearby corona. For the instrument team, that was a useful demonstration. For anyone trying to understand the picture, it was also a reminder that the dark circle in the centre is hiding an extremely active boundary. Things do not simply begin at the visible edge of the occulta. Plasma structures continue behind it. Magnetic loops connect back toward the sun. Prominences rise from lower levels. Material appears from behind the artificial disk and then moves outward through the area. SPIICS can observe. The closer the instrument can see to the true solar edge, the less of that early development is missing. This becomes very obvious when Proba 3 data are combined with observations from other spacecraft. On May 23, 2025, ESA created a composite view using 3 instruments. At the centre was the Sun and its low atmosphere, observed in ultraviolet light by the SWAP telescope aboard Proba 2. Surrounding that was the inner corona recorded by Proba 3's ASPIICS. Farther outward was the higher corona seen by the LASCO C2, coronagraph aboard SOHO. Placed together, the images formed something solar physicists had wanted for years: overlapping coverage from the solar disk outward through the inner corona and into regions where conventional coronagraphs work well. Before Proba 3, there was an awkward break in that coverage. Imagine 3 security cameras watching a long hallway. The first camera covers the entrance, the third covers the far end. Unfortunately, nobody installed the second camera. You can watch someone enter. Several minutes later, you can watch them appear near the exit. You know they crossed the middle. You can make reasonable guesses about what happened there. But if they changed direction, stopped, accelerated, met someone, dropped something, or performed an unexpected little dance, you would not know. The inner corona has been the missing camera. Solar imagers have watched activity near the visible sun. Coronagraphs have watched structures farther away. Proba 3 now gives scientists a much better chance to follow the same feature through the region between them. This matters because solar structures change quickly. A coronal mass ejection, for example, can begin close to the sun and grow rapidly as it moves outward. On July 16th, 2025, Proba 3 captured part of such an event. ESA later combined ASPIICS observations with Proba 2 and SOHO data to follow the eruption continuously across the different fields of view. The feature appeared near the edge of the solar disk, moved through the inner corona visible to Proba 3, and then continued into the higher corona covered by SOHO. The combined sequence ran for about an hour and a half. That continuity is more important scientifically than producing one especially sharp picture. A single frame gives position, several frames give motion, enough frames give speed. Follow the same feature for longer and you can begin measuring acceleration. Watch many different features and patterns start to appear. This is where Proba 3's artificial eclipses begin doing something natural eclipses cannot do practically. A natural total eclipse gives researchers a few minutes. That can produce exceptional images of fine coronal structure, and modern eclipse expeditions gather enormous amounts of useful information during those minutes. The problem is that the event ends just as the sun has begun doing something interesting. Proba 3 can maintain eclipse conditions for hours. By April 2026, ESA reported that the mission had already created 57 artificial eclipses since July 2025 and accumulated more than 250 hours of high-resolution video of the corona. ESA compared that total observing time with roughly 5,000 natural total eclipse campaigns on Earth. ASPIICS can normally acquire 1 or 2 images every minute, making it possible to turn the observations into time sequences showing motion through the inner corona. That changes the scale of the dataset completely. Imagine an astronomer studying a natural eclipse in which totality lasts 3 minutes. Now imagine asking for 5 hours. That is 100 times longer. During those hours, the corona does not politely maintain the same appearance. It changes, structures move, prominences shift, material flows along magnetic fields, loops brighten and fade. Plasma rises, breaks apart, and travels away from the Sun. The longer observing window turns the corona from a picture into an environment. One particularly useful sequence came from September 21st, 2025. Prober 3 observed the Sun during an active period for about 5 hours, taking an image every 5 minutes in one of its helium-sensitive channels. During that single observing window, ASPI-ICS captured 3 separate prominence eruptions. The structures began close to the Sun, expanded outward, and then broke apart as plasma moved into different regions of the corona. According to ASPI-ICS principal investigator Andrei Zhukov, capturing 3 such eruptions in one 5-hour period was unusual, and the long uninterrupted observing window made it possible to see them clearly. Think about what the instrument had to do during those 5 hours. The occultus spacecraft had to remain correctly aligned in front. The coronagraph spacecraft had to stay within the artificial shadow. The navigation sensors had to keep measuring the formation. Cold gas thrusters had to make small corrections. ASPI-ICS had to continue acquiring images. Its filters had to isolate the selected wavelength. The spacecraft had to store and later transmit the data. Then scientists on Earth had to calibrate the images, correct instrumental effects, combine exposures, and align the resulting frames with observations from other solar telescopes. The final animation might last only a few seconds on a computer screen. Behind those few seconds is an entire orbital ballet that solar researchers were previously forced to ask the Moon to perform. There is another advantage to having many repeated eclipses. Scientists can compare different kinds of solar conditions. The corona changes across the Sun's roughly 11-year activity cycle. During quieter periods, its large-scale magnetic structure can be more orderly. Near solar maximum, the magnetic field becomes more complex, active regions are common, and eruptions occur more frequently. One natural eclipse gives you the corona on one particular day. Prober 3 can return again and again. That allows researchers to watch the inner corona under different magnetic configurations, instead of treating each observation as an isolated event. It also gives computer models something they desperately need: data. Solar physicists build numerical models that try to reproduce the corona, using measurements of the Sun's magnetic field and equations describing plasma behavior. A model might predict where streamers should form. It might calculate how magnetic field lines open into interplanetary space. It might estimate density and temperature. It might simulate how an eruption expands. The obvious question is whether the simulated corona actually resembles the real one. Until now, comparisons close to the Sun have been limited because routine observations of the inner corona were limited. Prober 3 supplies a continuous stream of measurements in exactly that region. ESA has pointed out that these observations can be used to improve so-called digital eclipses, computer simulations that generate views of what the corona should look like. Researchers can compare a simulation with an ASPI-ICS image, find where the two disagree, adjust the model, and try again. That may sound less exciting than discovering a completely unexpected object. But most progress in solar physics happens through this quieter process. A model predicts a density, an image shows a different density, a theory predicts where material should move, a sequence shows it moving somewhere else, a calculation expects a certain acceleration, measurements return a larger one. Then researchers have to decide whether the model needs a small correction or whether something more fundamental is missing. ASPI-ICS is especially useful because its images are not only showing where material is, they're showing how different types of material relate to one another. The white light measurements trace electrons. Polarization helps isolate coronal scattering. The narrow band filters highlight plasma associated with particular spectral emissions. Data from Prober 2 and other solar missions add information at ultraviolet wavelengths. SOHO provides the higher corona. Put these together, and scientists get several overlapping views of the same physical system. It is somewhat like examining weather using ordinary photographs, infrared images, radar, wind measurements, and temperature maps. No single layer tells the complete story. Together, They reveal why the clouds are moving rather than merely confirming that clouds exist, and the first Clearprober 3 views made one fact difficult to ignore. The inner corona is busy. This may seem obvious. We already knew the sun was active. Solar observatories have shown spectacular flares and eruptions for decades. But there is a difference between knowing a region must contain motion and having enough continuous high-resolution observations to measure that motion directly. Features that look like thin stationary strands in one image may be changing over minutes. Small bright structures can travel outward. Plasma can accelerate. Material can reverse direction. A streamer that appears smooth at lower resolution may contain numerous small disturbances moving independently. That realization becomes increasingly important once the images are turned into videos, and researchers start tracking individual features frame by frame. The apparent serenity of an eclipse photograph can be misleading. The corona is not a fixed halo. It is an extremely hot magnetized plasma whose structure is being reorganized continuously. Its temperature alone tells us that something unusual is happening. The sun's visible surface is about 5,500 degrees Celsius. Move upward into the corona seen by ASP-IICS, and you encounter plasma around 1 million degrees, with some structures reaching 2 million degrees or more. ESA's ASP-IICS team describes the corona as roughly 200 times hotter than the solar surface in some of its observations. That is not a small discrepancy, and it cannot be explained simply by saying the sun is hot. If ordinary heat were flowing outward from the visible surface and nothing else were adding energy, temperatures should generally fall with distance. Instead, the outer atmosphere becomes dramatically hotter. For decades, researchers have proposed ways that magnetic fields could transport and release enough energy to produce this result. Some ideas involve waves carrying energy upward from the lower atmosphere. Others involve countless small magnetic reconnection events. Turbulence may transfer energy into ever smaller scales until particles can absorb it. Several processes may operate together. The important question is not whether the corona contains energy. It obviously does. The question is how that energy gets there, where it is deposited, and why the plasma becomes so extraordinarily hot just above a surface that is much cooler. Move away from a fire, and you expect to get colder. Move away from a stove, a radiator, or almost any other obvious source of heat, and the same thing happens. Energy spreads out, temperatures drop, and eventually you reach a point where the heat is barely noticeable. That expectation works inside the sun as well. Deep in the solar core, temperatures reach roughly 15 million degrees Celsius. That is where nuclear fusion occurs, converting hydrogen into helium and releasing the energy that eventually makes its way outward. As you travel from the core toward the visible surface, the temperature falls. By the time you reach the photosphere, the layer we normally think of as the sun's surface, the temperature is around 5,500 degrees Celsius. Still unpleasantly warm, obviously, but much cooler than the core. So far, everything behaves sensibly. Then you continue upward, and the temperature changes direction. Instead of becoming cooler, the solar atmosphere begins heating again. By the time you reach much of the corona, temperatures are commonly around 1 million degrees Celsius. In some structures, they can reach 2 million degrees or more. The corona that Prober 3 is now observing can therefore be roughly 200 times hotter than the visible solar surface directly beneath it. That is the coronal heating problem. And scientists have been trying to solve it since the extraordinary temperature of the corona became clear in the first half of the 20th century. The mystery is not simply that the corona is hot. The sun is a star. Finding hot material near it is not particularly shocking. The strange part is the temperature profile. Something has to carry energy from lower parts of the solar atmosphere into the corona and then deposit that energy there. Ordinary thermal conduction from the photosphere cannot explain a 1 million degree atmosphere sitting above a surface at about 5,500 degrees. Heat does not spontaneously flow from the cooler photosphere into a much hotter corona, and maintain that temperature difference. Some other source of energy has to be involved. The leading suspect has been obvious for a long time: magnetism. The sun is made largely of plasma, meaning the gas is hot enough for electrons to separate from atomic nuclei. Once matter becomes plasma, magnetic fields become enormously important to its behaviour, and the sun has magnetic fields everywhere. They rise through the photosphere, they form loops above active regions, they twist, they stretch, they reconnect, they extend outward into the solar wind. They can contain enormous amounts of stored energy. So the problem gradually became less about finding an energy source and more about understanding exactly how magnetic energy turns into heat. That distinction matters because several mechanisms can do it. The first major family of explanations involves waves. The solar surface is not still. Hot plasma rises, cooler plasma sinks. Convective motion churns continuously beneath the photosphere, producing the grainy pattern astronomers call granulation. Magnetic field lines threaded through this moving plasma are constantly being shaken. Imagine one end of a rope attached to something far above you. If you move the lower end sideways, a disturbance travels along the rope. Magnetic structures in the sun can transmit disturbances in a somewhat similar way. One particularly important type is called an Alfvén wave, named after Swedish physicist Hannes Alfvén. An Alfvén wave travels through magnetized plasma as particles and magnetic fields move together. There is no physical rope. The magnetic field provides the restoring force. Shake the field at one location and energy can travel along it. That makes Alfvén waves very attractive as a possible way to carry energy upward. The photosphere contains enormous amounts of mechanical motion. If some of that motion launches magnetic waves, those waves can travel away from the surface and into the corona. The important question is what happens next. Transporting energy upward is only half the problem. Somehow the wave energy has to be transferred into the particles themselves. Otherwise the waves would simply pass through without heating anything. Several things can interfere with them. Waves can reflect when they encounter changing plasma conditions. Different waves can travel in opposite directions and interact. Their energy can cascade into progressively smaller motions. Eventually, those small-scale motions can dissipate, converting organized wave energy into random particle motion. Random particle motion is what we measure as temperature. The broad idea is straightforward. Shake the magnetic field, send energy upward, break the motion into smaller scales, heat the plasma. The details are considerably less cooperative. Solar plasma is not uniform. Density changes rapidly with height. Magnetic field strength varies from one region to another. Open magnetic fields behave differently from closed loops. The corona contains structures ranging from enormous streamers to features far below the resolution of many telescopes. A wave travelling through that environment can reflect, refract, interact with other waves, or lose energy in different ways depending on local conditions. Researchers therefore need to know where the waves are, how much energy they carry, and how quickly that energy disappears. There is good evidence that these waves matter. Recent joint measurements from ESA's Solar Orbiter and NASA's Parker Solar Probe have strengthened the case that large-scale Alfvénic fluctuations provide an important source of energy for the far solar wind. Solar Orbiter observed the larger scale corona, while Parker directly sampled plasma farther along the flow, allowing researchers to compare the available wave energy with the energy required to heat and accelerate that wind. That is a major piece of the puzzle. It does not mean one kind of wave has solved the entire coronal heating problem everywhere on the sun. The corona is too varied for that conclusion. It means the energy carried by magnetic fluctuations is no longer just a convenient theoretical possibility. We can measure important parts of that process. There is another leading explanation, and this one begins with magnetic field lines becoming tangled. The visible surface of the sun is constantly moving. Different regions rotate at different speeds. Plasma flows around sunspots. Convective cells push magnetic footpoints in different directions. If you imagine magnetic loops anchored at both ends in that moving surface, those loops do not remain beautifully organised for long. Their geometry becomes stressed. They can twist around neighbouring fields. Energy accumulates. Eventually the configuration can become unstable. Then magnetic reconnection can occur. Reconnection is one of the most important processes in solar physics. Magnetic field lines are useful for visualizing magnetic structure, but they are not physical wires. Under certain plasma conditions, magnetic fields can rapidly rearrange their connectivity. When that happens, stored magnetic energy is released. Some goes into heat, some accelerates particles, some launches waves, some drives bulk plasma motion. Large reconnection events help power solar flares, but the corona does not need to rely only on enormous flares. Decades ago, physicist Eugene Parker proposed that the Sun might be producing vast numbers of much smaller energy releases, often called nanoflares. A nanoflare would be tiny compared with a major solar flare. That does not make it unimportant. If sufficiently small heating events occur constantly across the solar surface, their combined energy could be enormous. Think of rainfall. One drop contains almost no water. Millions of drops can flood a street. The same logic applies to small solar energy releases. One event may barely affect the corona. A continuous population spread across the Sun could help maintain temperatures above 1 million degrees. Solar Orbiter has provided intriguing observations related to this idea. Its extreme ultraviolet imager discovered large numbers of small, short-lived brightenings that researchers nicknamed campfires. Many lasted only tens of seconds and covered areas far smaller than ordinary large solar flares. Simulations indicated that at least some of these events could be produced by magnetic reconnection and could contribute to coronal heating. Again, the wording matters. Contribute, not necessarily explain everything. The Sun has been resisting one-sentence explanations for several billion years, and there is little evidence that it intends to stop now. It is entirely possible that different heating mechanisms dominate in different places. Magnetic reconnection may be especially important in one environment. Wave dissipation may dominate somewhere else. Turbulence can connect the two. Even the categories themselves overlap. A reconnection event can launch alpha waves. Alpha waves can interact and produce turbulence. Turbulence can generate small current sheets where reconnection occurs. The processes do not wait patiently in separate boxes while scientists decide which one deserves credit. They happen together. This brings us to turbulence. Turbulence is familiar if you have ever watched smoke twist through the air, seen water churn behind a rock in a river, or experienced a flight where the seatbelt sign remained on considerably longer than you would have preferred. A turbulent fluid contains motion across many different scales. Large structures feed energy into smaller ones. Those smaller structures feed even smaller motions. Eventually, the energy reaches scales where it can be dissipated. In ordinary fluids, viscosity converts that organized motion into heat. A magnetized plasma is much more complicated, but the general idea of an energy cascade still applies. Large magnetic and plasma motions in the corona can create smaller fluctuations. Those fluctuations interact. Energy moves toward progressively smaller scales. At sufficiently small scales, particles can absorb it. The plasma heats. For years, turbulence has been one of the strongest candidates for explaining at least part of the corona's extreme temperature. The challenge has been measuring the process well enough. You need information about large-scale motion. You need measurements of fluctuations. Ideally, you want direct plasma measurements as well. That is difficult when the laboratory is the atmosphere of a star. One useful opportunity came when Solar Orbiter observed the same broad coronal region through which Parker Solar Probe was travelling. Solar Orbiter supplied remote views of the large-scale corona, while Parker measured the plasma directly. Researchers used the combined observations to estimate how much energy turbulence was transferring into heat. The result provided strong evidence that turbulent dissipation could supply an important part of the heating required by the corona. That helps explain why scientists become so interested when a new instrument reveals small moving structures in the inner corona. Those structures are not just visual details, they can be evidence of the mechanisms moving energy through the plasma. Suppose an instrument shows a streamer that appears smooth. You might build a model in which plasma moves gradually along that streamer. Now increase the resolution and the cadence. The smooth structure breaks into many smaller features. Some move outward, some change shape, some accelerate, some interact. The apparently simple flow begins looking turbulent. Your model now has more work to do. This is exactly where Proba 3 becomes useful. SPICS is not a thermometer that directly measures the temperature of every coronal particle. Its special contribution is geometry. It can repeatedly observe the inner corona in visible light and selected spectral bands, close to the region where material is being heated and accelerated. That is the part conventional space coronagraphs have often struggled to monitor continuously. The corona seen in those images is not homogeneous. Hot loops appear. Prominences containing much cooler plasma rise into it. Streamers extend outward. Small structures move through larger structures. The boundaries between different magnetic regions shift. Because Proba 3 can hold an artificial eclipse for hours, scientists can watch how these features evolve instead of relying on a brief natural eclipse or isolated snapshots. That difference becomes especially important when testing heating theories. Consider the wave idea. If waves are carrying substantial energy through the inner corona, their effects should influence motions and structures there. Researchers can compare observed behavior with models predicting how disturbances propagate along magnetic fields. They can examine whether different regions behave as expected. They can compare open magnetic structures, where plasma can escape into the solar wind, with closed loops that remain connected to the sun at both ends. The reconnection picture also makes observational predictions. Magnetic rearrangement can create local brightenings, jets, rapidly changing loops, and moving plasma structures. No coronagraph image by itself can prove that every small feature was produced by reconnection, but long sequences can show where changes occur, how quickly they develop, and how material responds afterward. Then those observations can be combined with ultraviolet measurements of the lower corona and magnetic information from the visible surface. The same is true for turbulence. A turbulent environment should not look perfectly smooth when examined at sufficient resolution and cadence. Researchers want to measure how structures vary with size. They want velocities. They want acceleration. They want to know whether small disturbances increase or decrease as plasma travels outward. Those quantities place limits on how much energy is being transferred through the system. There is another reason the heating problem and the solar wind problem are difficult to separate. A 1,000,000-degree corona cannot simply sit there indefinitely. Hot plasma has pressure. That pressure contributes to the corona expanding outward. In the 1950s, Eugene Parker showed mathematically that a corona this hot should produce a continuous outflow. That prediction became the solar wind. A few years later, spacecraft measurements confirmed that charged particles really were streaming outward from the Sun through interplanetary space. So the mechanism heating the corona is related to the mechanism driving the solar wind. Put energy into particles and waves in the corona, and some of that energy can appear as temperature. Some can appear as outward motion. The same magnetic activity may help produce both. This is why solar physicists often discuss coronal heating and solar wind acceleration in the same sentence. They are not identical problems, but they share the same environment and many of the same physical processes. Imagine heating a gas inside a container. If the container is sealed, increasing the energy mainly changes temperature and pressure. Now remove part of the container, some of the gas escapes. The way energy is divided between heating and bulk motion becomes part of the problem. The corona does not have a solid roof. Along magnetic field lines that open into space, plasma can flow outward. That flow becomes the solar wind. Along closed field loops, particles can remain confined and become extremely hot. Different magnetic geometries can therefore produce different combinations of temperature and outflow. Coronal holes are a good example. These regions contain magnetic field lines that extend outward into interplanetary space rather than closing back onto the Sun nearby. They're associated with fast solar wind. Other regions contain large streamers and closed magnetic structures. The plasma behaves differently. A complete solution to the heating problem has to explain not only how the corona reaches 1,000,000 degrees, but why different parts of it behave differently while receiving and redistributing magnetic energy. That is why a simple phrase like magnetic fields heat the corona is true but unsatisfying. It is roughly equivalent to saying engines make cars move. Yes. We would still like to know what happens between the fuel tank and the wheels. Solar researchers want the equivalent mechanical diagram. Where is magnetic energy stored? How is it transported upward? How much arrives as waves? How much is released through reconnection? At what scales does turbulence become important? Where do particles absorb the energy? Do electrons and ions receive equal amounts? Does the dominant process change between active regions, quiet regions, and coronal holes? How does the answer change over the solar cycle? And how much of the same energy ultimately appears as the speed of the solar wind? Those are not questions one spacecraft can answer alone. Proba-3 is part of a much larger network of observations. Solar Dynamics Observatory watches the Sun in multiple wavelengths from near Earth. Solar Orbiter studies the surface, corona, magnetic environment, and solar wind from much closer to the Sun. Parker Solar Probe has repeatedly entered the corona and directly sampled particles and magnetic fields. SOHO continues observing the outer corona after decades in operation. Ground-based solar telescopes provide extremely detailed measurements of the photosphere and chromosphere. Natural eclipses still offer exceptional views. Proba-3 adds something specific to that collection. Long, repeatable, visible light observations of the inner corona. That fills a gap between the low solar atmosphere and the outer regions seen routinely by conventional coronagraphs. And because those observations overlap with other missions, researchers can follow structures across instruments. A feature can appear close to the solar surface in ultraviolet images. It can move into the inner corona observed by ASPIICS. Then it can continue outward into the field of another coronagraph. Eventually a spacecraft may sample the resulting solar wind directly. Instead of studying separate locations and assuming how they connect, scientists can increasingly try to follow the connection itself. There is an important limitation here. Proba-3 has not suddenly solved the coronal heating problem. No responsible solar physicist opened the first ASPIICS image, pointed at one bright strand, and announced that a century-old mystery could now be removed from the list. The mission provides new observations. Those observations have to be measured carefully. Velocities have to be extracted. Structures have to be identified across successive frames. Models have to be compared with the data. Results have to be checked against observations from other instruments. That work takes time because the corona contains overlapping plasma along every line of sight. What looks like one feature in a two-dimensional image may actually contain several structures at different distances from the Sun. Brightness can depend on density as well as geometry. A moving pattern is not always identical to the motion of the particles producing it. Solar physicists have to separate those effects before turning a beautiful movie into a physical measurement, and that is exactly what began happening as the Proba-3 observations accumulated. The apparently quiet inner corona was hiding motion that was much faster, much more irregular, and much more complicated than older observations had been able to show. That became clear when researchers stopped treating the Proba-3 images as photographs and started turning them into measurements. One picture of the corona can show a streamer. Take another picture 30 seconds later, and a faint knot inside that streamer may have moved. Take another 30 seconds after that, and it has moved again. Once the same feature can be identified across enough frames, its position can be plotted against time. From that, scientists can estimate its speed. If the speed changes, they can measure acceleration. If the feature begins moving back toward the Sun instead of outward, that becomes visible too. This is one of the advantages ASPI-ICS was built to provide. During suitable observing sequences, it can take images at cadences as short as about 30 seconds, while resolving fine structures at roughly 5.6 arcseconds. The instrument covers the corona from close to 1.1 solar radii out to about 3 solar radii, giving researchers an unusually detailed view of the region where the slow solar wind is thought to form. And when scientists examined that region carefully, it did not behave like a smooth stream of plasma steadily flowing away from the sun. It looked busy. There were small, bright blobs moving outward. There were darker structures moving inward. There were narrow jets. There were waves. Some features accelerated, others slowed down. Different motions sometimes appeared in the same part of the corona at nearly the same time. Researchers studying the first ASPI-ICS sequences described these small-scale dynamics as widespread and persistent. They could see weak outflows and inflows across much of the corona between roughly 1.3 and 3 solar radii, including features only a few thousand kilometers across. Some were so faint that their brightness differed from the surrounding corona by only around 1 or 2%. That is a surprisingly small signal. If you were looking at an ordinary photograph and one patch was 1% brighter than the background, you would probably not notice it. ASPI-ICS can. More importantly, it can notice the same faint patch again 30 seconds later. That turns a tiny brightness variation into a moving object that can be followed through the corona. The first detailed study of these motions was published in the astrophysical journal Letters in March 2026. Researchers led by Andrei Zhukov of the Royal Observatory of Belgium tracked a collection of these small plasma structures and compared their motion with expectations based on earlier observations. The numbers immediately stood out. Previous measurements suggested that slow solar wind close to the sun should typically be moving at around 100 km per second. Proba 3 saw some plasma blobs moving between roughly 250 and 500 km per second. In other words, parts of what researchers associate with the slow solar wind formation region were moving 3 to 4 times faster than expected. There is an amusing problem with calling something moving at 500 km per second slow. At that speed, you could cross the distance from London to New York in about 11 seconds, assuming air traffic control was feeling unusually cooperative. But fast and slow solar wind are relative terms. Far from the sun, the slow solar wind generally travels at several hundred kilometers per second, while the fast solar wind can reach roughly 700 or 800 kilometers per second. The mystery is not that the slow wind eventually becomes fast by everyday standards. We already knew that. The surprise is how quickly some of its structures appear to be moving while they're still comparatively close to the sun. Older observations had suggested a more gradual acceleration. The new Proba 3 measurements indicate that at least some pieces of the flow can already be travelling at several hundred kilometers per second in the inner corona. That changes where scientists have to look for the acceleration. If a runner is already sprinting when you first see them 50 meters from the starting line, then whatever caused the sprint probably happened earlier. The same logic applies here. If plasma structures are already moving at 250, 400, or even around 500 kilometers per second close to the sun, then a substantial amount of energy has already been transferred into their motion. The acceleration process cannot be treated only as something happening gradually farther out. Some of it may begin very low in the corona. There was another surprise hidden in the data. The plasma did not all move outward. ASPI-ICS also recorded numerous inflows. Some dark features moved back toward the sun at around 100 kilometers per second. In a few cases, faster inward-moving structures slowed dramatically as they descended, falling from speeds of several hundred kilometers per second toward roughly 100 kilometers per second over the course of about an hour. Researchers could track them moving from around 3 solar radii to below 2 solar radii. That matters because the word solar wind can make the corona sound like a one-way system. Wind leaves the sun, therefore everything should move outward. But close to the sun, the situation is not that simple. The large-scale solar wind is outward. At smaller scales, the magnetic environment can produce motions in both directions. Material can be released, other material can fall inward, magnetic structures can reconnect, loops can shrink, plasma can be redirected, waves can move through the region independently of the bulk flow. The inner corona is not yet a fully organized river of particles heading into interplanetary space. It is closer to the region where that river is being assembled. Researchers sometimes refer to this complicated zone as the solar turbosphere. The term describes a region where the outward solar wind has not yet become overwhelmingly dominant, and where smaller inflows, outflows, waves, and magnetic disturbances can coexist. The first ASPIICS observations give unusually direct visible light evidence of just how complicated that environment can be. A useful comparison is the beginning of a river in the mountains. Far downstream, the direction is obvious. The water flows toward the sea. Stand near the source, however, and you may see water coming from several channels. Small currents meet. Some swirl backward behind rocks. Pools circulate. Water drops from one level to another. Local motion can briefly point in almost any direction, even though the total flow eventually moves downhill. The solar wind seems to have something of the same problem, except the rocks are magnetic fields and the water is plasma at temperatures around 1,000,000 degrees. The streamers Proba 3 observes are especially important. A solar streamer is one of the large, bright structures extending outward through the corona. They can be seen clearly during natural eclipses as long, pale rays surrounding the blocked sun. Their shape is controlled by the solar magnetic field. Near the sun, many field lines inside a streamer are closed, connecting back to the solar surface at both ends. Farther out, the magnetic geometry changes. Near the top of a streamer, field lines can become stretched outward and interact with open magnetic fields connected to interplanetary space. This boundary is one of the places where scientists think variable, slow solar wind may be released. One proposed mechanism is interchange reconnection. Suppose you have one magnetic field line that loops back to the sun and another that extends outward into space. Under suitable conditions, those magnetic configurations can reconnect. Their connections change. Plasma that was previously trapped on a closed field can suddenly find itself connected to a route leading outward. The material escapes. The magnetic geometry rearranges. A small blob of denser plasma may be released into the solar wind. Repeat that process many times across a complicated magnetic boundary, and the slow wind may emerge not as one steady flow, but as a constant collection of small releases. Proba 3's images fit intriguingly well with that general picture. The researchers saw many small blobs and jets associated with streamers and pseudo-streamers. Some outflows were frequent enough that roughly 10 separate events could be distinguished within one narrow sector during only an hour of observations. They were also much smaller than the larger blobs traditionally identified farther out by instruments such as SOHO's LASCO coronagraphs. That difference could explain why this activity appeared less obvious before. Farther from the sun, small structures expand. Several nearby disturbances may merge. Only the larger or brighter ones remain easy to identify. An instrument observing mainly the outer corona may therefore see the surviving large features without revealing how many smaller disturbances existed closer to their origin. Proba 3 is looking earlier, and when you look earlier, what seemed like one large event farther away may begin to break into many small events. There is a similar effect in weather. From a satellite, a storm system can appear as one enormous cloud structure. Fly through it, and the storm contains individual updrafts, downdrafts, rain bands, turbulent cells, and local wind changes. The large structure is real, so are the smaller ones. You simply need the right scale of observation to see them. ASPIICS is changing the scale at which solar researchers can routinely examine the inner corona. One particularly interesting feature was a wide helical jet observed inside a pseudo-streamer. Rather than moving outward at a constant speed, the structure accelerated dramatically. Measurements indicated that its radial motion increased from only about 40 kilometers per second to around 400 kilometers per second. That is a tenfold increase. The jet also contained threads that moved sideways as well as outward. Close to the Sun, the non-radial motion could be comparable with the outward motion. Farther away, the radial component became dominant. That is the sort of observation theorists like because it gives them several things to explain at once. Why did the jet begin there? Why was it twisted? Why did it accelerate so strongly? Why did its sideways motion change as it moved outward? What magnetic configuration produced it? How much energy was released? And did the material eventually become part of the solar wind measured farther from the Sun? A model that explains only the final speed is not enough. It also has to reproduce the path taken to reach that speed. Other features behaved differently. Some bright outflows travelled between roughly 100 and 400 kilometers per second without showing an obvious smooth acceleration. Certain disturbances propagated even faster. Across the larger set of small-scale dynamic features studied in the 2026 paper, measured speeds extended from only a few tens of kilometers per second to more than 500 kilometers per second. The structures included blobs, jets, waves, inflows and outflows, rather than one uniform population doing the same thing. That variety is important. It would be easier if the corona contained one type of object moving at one predictable speed. Scientists could measure a few examples, build a tidy average and go home early. Instead, Proba 3 found a wide distribution. Some features were slow, some were fast, some moved outward, some moved inward, some accelerated, some decelerated. Several types could coexist in the same broad region. This does not necessarily mean every feature represents a separate physical mechanism. Projection complicates the measurements. ASPI-ICS sees a two-dimensional image of a three-dimensional corona. A structure moving partly toward or away from the spacecraft may appear slower across the image than it really is. Several unrelated structures can overlap along the same line of sight. Brightness changes can sometimes make a feature appear to move even when the underlying plasma motion is more complicated. Researchers have to account for those uncertainties. Even with those limitations, the overall result remains clear enough. The slow wind formation region contains much more fine-scale motion than the older picture of a smooth, gradual outflow suggested. There is another reason that word turbulent has to be used carefully. In everyday language, turbulent simply means chaotic. In physics, turbulence has a more specific meaning. A turbulent plasma contains interacting fluctuations across many different spatial and temporal scales. Large motions transfer energy into smaller motions. Magnetic fields fluctuate. Velocity changes. Waves interact. The energy can cascade down towards scales where individual particles absorb it. That process may contribute both to heating the corona and to accelerating the solar wind. The small structures seen by ASPI-CS are not by themselves proof that one textbook turbulence model explains everything happening there. What they do show is exactly the kind of fine-scale variable environment in which simple steady flow descriptions become inadequate, and there is plenty of energy available to make the region complicated. Magnetic fields emerging from the Sun are continually moved around by plasma below the photosphere. Closed and open magnetic regions interact. Large streamers surround current sheets, where the magnetic field changes direction. Reconnection releases stored magnetic energy. Waves travel along field lines. Plasma pressure pushes material outward. Gravity pulls it inward. All of those effects are acting within the same few solar radii. It would almost be more surprising if the result were smooth. The reason earlier models sometimes look smoother is partly observational. Scientists have always known that the corona contains variability. Natural eclipses reveal fine strands. Older coronagraphs have detected blobs moving through streamers. SOHO, Stereo, Solar Orbiter, Parker Solar Probe and other missions have shown enormous complexity in the solar atmosphere and wind. Proba 3 is not replacing all of that work. Its contribution is to bring high cadence and relatively fine spatial resolution into a region that has been especially difficult to observe continuously. The original ASPI-ICS results emphasise that weak, widespread, small-scale inflows and outflows between roughly 1.3 and 3 solar radii were being seen with this combination of detail for the first time. That distinction is worth keeping. The plasma was not previously non-existent. We were not watching an empty corona in 2024 and then discovering turbulence when Proba 3 arrived. The structures were there, our ability to follow them was limited. This happens repeatedly in astronomy. Jupiter did not acquire storms when telescopes became better. Galaxies did not suddenly grow detailed spiral arms when larger mirrors were built. The universe becomes more complicated as our measurements improve because features that were once averaged together begin separating into individual pieces. Proba 3 has done something similar to the inner corona. A streamer that once appeared to contain a broad outward flow can now reveal a procession of smaller density structures. A region assumed to be mainly outward moving can contain measurable inflows. A predicted speed near 100 km per second can sit beside an observed blob racing at several hundred. The average has not necessarily become useless, it has become incomplete. That can have consequences for how we interpret spacecraft measurements farther away. By the time the solar wind reaches Parker Solar Probe, Solar Orbiter, or eventually Earth, it has travelled through millions of kilometres of space. Structures expand, they interact. Fast parcels overtake slower ones. Magnetic fields twist and stretch. Waves propagate through the flow. A spacecraft sampling the solar wind directly measures whatever has survived that journey to its particular location. Proba 3 provides an earlier view. It sees some of the structure before the long trip outward has had time to reorganize it. Connecting those two types of measurements could become extremely powerful. Suppose ASPI-ICS sees a series of small plasma releases leaving a particular streamer. Later, a spacecraft farther out measures a patch of unusually variable, slow solar wind associated with the same magnetic region. If researchers can connect those observations reliably, they can begin tracing the wind backward from the spacecraft to its source. That is one of the central goals of modern heliophysics. We already know the solar wind comes from the Sun. The interesting question is exactly which parts of the Sun produce which parts of the wind. Fast solar wind is comparatively well associated with coronal holes, regions where magnetic field lines are open and extend outward. The variable slow solar wind is more difficult. Its composition and magnetic properties suggest that at least some of it comes from plasma that was previously confined closer to the Sun. Streamers, pseudostreamers, and complicated boundaries between open and closed fields are therefore major suspects. Proba 3 is watching those suspects much more closely. The timing of the observations is also useful because the Sun is near the active portion of its roughly 11-year cycle. Around solar maximum, the Sun's magnetic field becomes much more complicated than it is near minimum. Streamers can extend in many directions instead of being concentrated mainly around a simpler equatorial belt. Active regions are common, eruptions are frequent. For ASPI-ICS, this means the field of view contains a particularly rich collection of magnetic environments. ESA's first science analysis noted that streamers carrying slow wind structures were appearing around many sides of the Sun during this active phase, giving researchers opportunities to compare motions in different regions. As activity declines over the coming years, the corona should reorganize. The large-scale magnetic field becomes simpler. Fast wind-producing coronal holes are expected to become more prominent around the poles. Slow wind structures should become more concentrated around lower latitudes. Proba 3 can therefore study not only one turbulent corona, but how the small-scale dynamics change as the solar cycle evolves. That could help separate temporary behaviour from persistent mechanisms. If a particular type of blob appears only during highly active magnetic conditions, that tells you something. If the same process remains widespread even during quieter conditions, That tells you something else, and there is a great deal of data still waiting to be examined. By April 2026, Probe 3 had already accumulated more than 250 hours of high-resolution coronal video from 57 artificial eclipses. ESA stressed that much of that material had not yet been fully analysed when the first slow solar wind results were announced. So the speeds of 250 to 500 kilometers per second were not the conclusion of the mission. They were among the first measurements from a new observing capability. That is a useful way to think about Probe 3. The most important result may not be one particular number. It may be that scientists finally have enough continuous observations to stop describing the inner corona mainly through averages. Averages are useful. They tell us the typical density, the typical speed, the typical brightness, the typical acceleration. But plasma does not care what is typical. A small reconnection event can release material much faster than the average. A local magnetic structure can drive an inflow while the surrounding corona moves outward. A narrow jet can accelerate by hundreds of kilometers per second. A wave can travel through the same region without carrying the same material with it. Those details are where the physical mechanisms reveal themselves. The first Probe 3 results therefore complicate the picture in a productive way. The slow solar wind no longer looks quite so much like a gentle flow that gradually gathers speed as it moves away from the sun. The question is where that outward motion actually becomes the solar wind. It sounds as though there should be a clear boundary. Below this line, corona. Above this line, solar wind. Nature has not provided one. The solar wind is simply part of the sun's atmosphere that keeps expanding instead of remaining gravitationally bound. Plasma in the corona gains enough energy to travel outward along magnetic fields, accelerates as it goes, and eventually spreads throughout the solar system. By the time that plasma passes Earth, about 150 million kilometers from the sun, there is no question that it is solar wind. Spacecraft near our planet measure streams of protons, electrons, helium nuclei, magnetic fields, waves, and disturbances flowing past us continuously. Closer to the sun, the distinction becomes less obvious. You find plasma that is already moving outward but is still accelerating. You find magnetic loops where material remains trapped. You find open magnetic fields that provide routes into interplanetary space. You find blobs moving outward at hundreds of kilometers per second beside structures that are moving back toward the sun. Somewhere inside that complicated environment, the sun's hot atmosphere becomes the wind. Scientists have known that this must happen since long before they could observe the starting region properly. In 1958, astrophysicist Eugene Parker published a mathematical model of the solar atmosphere. At the time, many scientists assumed that the corona could remain more or less static around the sun. Parker's equation said otherwise. If the corona really was heated to temperatures of 1,000,000 degrees or more, its pressure would be too great for the atmosphere simply to sit there in equilibrium. The hot plasma would expand outward, and it would keep expanding. The result would be a continuous wind of solar material flowing into space. That idea was controversial. The term solar wind itself sounded unusually literal for something happening in space, where there is obviously no ordinary air. Then spacecraft began measuring exactly what Parker had predicted. Luna 1 detected signs of the flow in 1959. NASA's Mariner 2 made more definitive measurements in 1962, and found that the wind was not even moving at one constant speed. There were faster streams, there were slower streams. And suddenly, the solar system looked quite different. The planets were not moving through empty space with the sun sitting quietly at the centre. They were moving through an enormous expanding atmosphere generated by the sun. That atmosphere extends well beyond the orbit of Earth. It passes Mars. It travels beyond Jupiter and Saturn. Eventually, much farther out, it encounters material between the stars and forms the distant boundary of the heliosphere. Earth spends its entire existence inside this flow. The sun never switches it off. Even during periods when the visible solar surface appears relatively quiet, charged particles continue streaming outward. If you could somehow stand in interplanetary space with a sufficiently strange windsock, there would almost always be something for it to point at. The important question is what gives that material its speed. Parker's original model showed that a sufficiently hot corona naturally expands, and that thermal pressure is a fundamental part of the process. But modern measurements show that heating alone is not the full story. Magnetic fields matter. Waves matter. Turbulence matters. Reconnection matters. And the amount each contributes can change depending on which part of the sun the wind comes from. Solar physicists commonly divide the wind into two broad categories. Fast solar wind can reach roughly 700 to 800 kilometers per second. Slow solar wind is often closer to 300 to 500 kilometers per second by the time it is measured farther from the sun. Those labels are relative. At 400 kilometers per second, slow solar wind would travel around Earth in about 100 seconds. It is only slow because the other variety is faster. The fast wind has a comparatively clear connection to regions called coronal holes. Coronal holes appear dark in extreme ultraviolet and X-ray images because their plasma is less dense and somewhat cooler than surrounding coronal regions. More importantly, their magnetic fields tend to be open. An open magnetic field line is anchored to the sun at one end and extends outward into the heliosphere at the other. For plasma trying to leave, that is useful. Instead of being trapped inside a magnetic loop that returns to the solar surface, particles have a path leading outward. Observations since the 1970s have linked these open-field, coronal holes with fast solar wind. The slow wind has been harder to explain. Some of it also comes from open magnetic field. It has to, because by the time plasma reaches interplanetary space, it cannot still be trapped on a small closed loop connected to the sun at both ends. The uncertainty concerns where those open field lines originate and how plasma gets onto them. One important possibility involves the boundaries between closed and open magnetic regions. Imagine a large magnetic loop. Plasma inside it is confined. Beside that loop is an open field line extending into space. If those magnetic fields reconnect, their connectivity changes. Material that was previously trapped can suddenly find itself attached to an open route. That material can escape. This process, often called interchange reconnection, may happen repeatedly around streamer boundaries and other complicated magnetic regions. Instead of a smooth tap being turned on, the slow solar wind may be released through thousands of small magnetic rearrangements. That would naturally produce blobs, jets, bursts, changes in density, changes in speed, exactly the kind of irregular structures Proba 3 has started seeing. Before ASPIICS, researchers had already observed larger blobs moving outward through streamers farther from the sun. The question was what those structures looked like closer to where they were released. Now the artificial eclipses allow scientists to watch much nearer to the source, and the first measurements suggest that the acceleration is not behaving quite as expected. Earlier estimates based on observations available farther from the sun suggested that slow wind material near the inner corona might typically be moving at roughly 100 kilometers per second. The Proba 3 measurements showed individual structures travelling at 3 to 5 times that speed in some cases. ESA's April 2026. Analysis showed plasma blobs moving at several hundred kilometers per second, where an older 2009 empirical speed profile predicted much slower flow. This does not mean every piece of slow solar wind leaves the sun at 500 kilometers per second. The measurements contain a broad range. Some features are much slower, some accelerate strongly, some appear to maintain high speeds, some move inward. Projection affects the measured velocities because ASPIICS observes motion across the plane of the sky rather than recovering every component of a feature's three-dimensional velocity. Still, the fast structures are difficult to dismiss. Something has already given them substantial energy. That pushes the scientific attention inward. Where did the acceleration happen? Was the plasma launched by magnetic reconnection? Did waves transfer momentum into it? Did pressure gradients accelerate it? Did turbulence contribute? Or are several of these mechanisms operating together? To understand why that distinction matters, imagine watching a car enter a motorway. If you first see it moving at 30 km per hour and later measure it at 100, you know most of the acceleration happened somewhere between those points. If your new camera reveals that the car was already travelling at 95 km per hour almost immediately after entering the road, then the location of the interesting event changes. You need to move your camera closer to the entrance. Prober 3 has effectively moved the camera closer. Parker Solar Probe approaches the same problem from the other direction. Instead of looking remotely at the corona from far away, Parker flies through the sun's outer atmosphere and measures the plasma directly. It records particle velocities, temperatures, densities, electric fields, magnetic fields, waves. Unlike ASPIICS, it does not simply watch a feature move across an image. It can fly into the material and measure what that material is doing at the spacecraft. That has produced its own surprises. When Parker first explored the near-sun solar wind, researchers expected conditions to become more orderly as the probe approached the source. Instead, the spacecraft encountered frequent sudden reversals in the magnetic field. These became known as switchbacks. During a switchback, the magnetic field rapidly bends back on itself while plasma velocity can increase at the same time. Rather than finding a simple outward field carrying a steady wind, Parker discovered a flow filled with magnetic kinks and bursts. The switchbacks became particularly interesting because they may contain energy that helps accelerate the solar wind. Think of the magnetic field as being disturbed by a sudden kink. That kink can carry energy. As it travels outward and interacts with the surrounding plasma, some of that magnetic and wave energy can be transferred into particle motion. Parker's observations also helped researchers trace groups of switchbacks back toward magnetic funnels rooted near the visible solar surface, especially around boundaries between large convective structures called supergranules. Those magnetic funnels appear to be important pathways through which energy and plasma escape upward. This begins to connect the pieces. At the surface, convection moves magnetic footpoints. Magnetic fields become stressed. Reconnection and waves release energy. That energy travels upward. The corona is heated. Some field lines open into space. Plasma begins escaping. Switchbacks and other disturbances propagate through the developing wind. Small blobs and jets move through the inner corona. Farther out, those separate structures gradually become the solar wind that spacecraft measure near Earth. The difficult part is proving exactly which event at the Sun became which structure farther away. Space is large. The Sun rotates. Magnetic fields curve. The solar wind changes while it travels. Two parcels released near each other can follow different magnetic paths. A fast stream can catch a slower stream. Waves move through the plasma. Individual structures expand. By the time something reaches Earth several days later, tracing it back to one small feature near the Sun can be extremely difficult. This is why different spacecraft are useful in combination. Prober 3 watches the inner corona. Solar Orbiter can observe the Sun remotely, while also measuring solar wind particles and magnetic fields around the spacecraft. Parker Solar Probe samples the corona and near-Sun wind directly. Other coronagraphs follow structures farther outward. Near-Earth spacecraft measure what eventually arrives here. Each mission sees a different part of the journey. The goal is to connect them. Suppose Prober 3 sees a small blob released from the edge of a streamer. Its position is measured, its speed is measured, its acceleration is estimated over several frames. A magnetic model can then be used to calculate which field line that structure may be following. Farther out, Solar Orbiter or Parker may cross material connected to the same broad solar region. Particle composition can provide additional clues. Magnetic polarity provides another. The timing provides another. None of these pieces alone guarantees that researchers have followed the exact same packet of plasma. Together, they narrow the possibilities. This approach is often called connection science. Instead of studying the sun and the solar wind as separate subjects, researchers try to connect a remote feature on the sun with an in situ measurement made by a spacecraft later. For solar wind research, that is particularly valuable because plasma composition can preserve information about where it originated. Different parts of the solar atmosphere contain different ratios of elements and ionization states. If a spacecraft measures those properties in the wind, researchers can compare them with the conditions expected in different solar source regions. It is a little like analysing water downstream to work out which tributaries contributed to it. Except your river is moving at hundreds of kilometers per second and is made of electrically charged particles connected to a rotating magnetic star. The sun rarely chooses the easy version of an experiment. Another important boundary in the solar wind is the Alfvén critical surface. Close to the sun, the magnetic field has a strong influence on the plasma. Disturbances called Alfvén waves can travel both outward and, under some conditions, back toward the sun. Farther out, the solar wind eventually becomes so fast that it exceeds the local Alfvén speed. Beyond that critical region, information carried by those waves can no longer easily propagate back upstream toward the sun. The wind has become more decisively detached. Parker Solar Probe crossed into the corona in 2021 by passing below this Alfvén critical boundary, and it discovered that the boundary was not a smooth sphere around the sun. It had peaks and valleys. The corona's outer edge was structured. That was another warning against assuming that solar wind acceleration happens in neat concentric layers. Different magnetic regions can reach these transitions at different heights. One part of the corona may already contain a rapidly escaping flow, while a neighbouring region still contains closed fields and trapped plasma. That helps explain why Proba 3 can see outward and inward motions beside each other. The inner corona is not one uniform atmosphere slowly becoming one uniform wind. It is a collection of magnetic environments. Some are releasing plasma, some are holding it, some are exchanging material, some are restructuring. Eventually the outward component wins. Gravity becomes less dominant. The solar wind becomes established. By the time it reaches Earth, the local back and forth motion close to the sun has been reorganized into a largely outward flow. But the wind still carries evidence of its complicated beginning. Switchbacks survive, density structures survive, fast and slow streams remain different. Magnetic sectors preserve information about their solar origins. The wind is therefore not just material leaving the sun, it is a record. Parker reads that record directly. Proba 3 is trying to watch parts of it being written. This is also where the temperature problem from earlier becomes inseparable from the acceleration problem. If magnetic waves carry energy upward and dissipate, part of that energy becomes heat. If they transfer momentum, part becomes outward motion. If reconnection releases magnetic energy, it can heat plasma, accelerate particles, and launch disturbances simultaneously. A mechanism does not have to choose between heating the corona and driving the solar wind. It can contribute to both. That is why the unexpectedly high Proba 3 speeds matter beyond one new velocity measurement. They tell researchers that the energy conversion is already advanced surprisingly close to the sun. Whatever is accelerating those structures is not waiting until the outer corona. It is working in the region ASPEICS can now observe. The first results also suggest that slow solar wind may deserve its reputation for being difficult. Fast wind has the relative convenience of being strongly associated with coronal holes. Slow wind can emerge from streamers, pseudo-streamers, boundaries between open and closed magnetic regions, and perhaps several different physical processes. It may not have one source. Its variability may be fundamental rather than accidental. If slow wind is assembled from repeated small magnetic releases, then expecting it to behave like a smooth continuous flow may have been the wrong starting assumption. The individual blobs Proba 3 sees could be pieces of that assembly process. Over time they expand and merge. Farther from the sun, a spacecraft sees what looks more like a continuous wind. Close to the Sun, ASPIECS sees the ingredients before they have blended together. It is similar to watching traffic. From high above a motorway, the cars can look like one continuous stream. Stand beside an entrance ramp and you see how that stream is made. One car joins, then another. A gap, 3 more, a truck. Someone merges badly and causes everyone behind them to reconsider their life choices. The average traffic flow is real, but the local process is much more irregular. The solar wind appears to have its own version of merging traffic. Except sometimes, one of the cars is travelling back toward the Sun. Over the next several years, Proba 3 should provide observations under different solar conditions. The Sun is moving away from the active maximum portion of its approximately 11-year cycle. As its magnetic configuration changes, the locations of streamers, coronal holes, and open-field boundaries will change too. That gives scientists a useful experiment. Do the unusually fast inner corona blobs remain common? Do their speeds change? Do inflows become less frequent? Does the structure of the slow wind simplify when the global magnetic field becomes more organized? How do the properties of features near streamer boundaries compare with those near coronal holes? A single observing campaign cannot answer those questions. Repeated artificial eclipses can begin to. The volume of data matters here. Natural eclipses are excellent at revealing fine structure, but happen under different conditions years apart. Proba 3 can return to the inner corona repeatedly using the same instrument and the same basic observing geometry. That consistency makes comparisons more useful. One observation tells you what happened. Many observations tell you what normally happens, and once researchers know what is normal, unusual events become easier to identify. That is exactly where another major solar mystery begins. The solar wind is always leaving the Sun, but every so often the corona does something much more violent. A large magnetic structure becomes unstable, an enormous amount of plasma is thrown outward, and what had been part of the solar atmosphere begins expanding through space as a coronal mass ejection. A CME can contain billions of tons of material. It can spread across a region larger than the Sun itself. Some travel at a few hundred kilometers per second. The fastest can exceed 1,000 kilometers per second. And unlike the ordinary solar wind, which is continuously present, a coronal mass ejection is an event. Something happens in the Sun's magnetic field. The corona reorganizes, and a large cloud of plasma begins moving away. The difficult part is understanding exactly what happens first. Solar eruptions are often discussed alongside flares because the two can occur together, but they are not the same thing. A solar flare is primarily a rapid release of energy in the Sun's atmosphere. Magnetic energy is converted into heat, radiation, accelerated particles, and plasma motion. X-rays and ultraviolet radiation can increase dramatically. A coronal mass ejection is the physical expulsion of a large magnetized plasma structure into space. You can have a powerful flare associated with a CME. You can also have flares without major CMEs and CMRs without especially impressive flares. The relationship depends on the magnetic configuration around the active region. This matters because the things that affect Earth arrive on different timescales. Radiation from a flare travels at the speed of light and can reach Earth in roughly 8 minutes. Energetic particles may arrive later. A CME usually requires somewhere from less than a day to several days to cross the distance between the Sun and Earth, depending on its speed and the solar wind it encounters along the way. So when scientists talk about forecasting space weather, they are really dealing with several related processes unfolding at different speeds. For coronal mass ejections, the first job is figuring out what caused the eruption and how quickly the structure begins accelerating. The Sun's magnetic field provides most of the energy. Near an active region, magnetic loops can store enormous amounts of it. The loops are anchored in plasma near the solar surface, and those anchor points are constantly moving because the Sun is not rigid. Plasma circulates. Different latitudes rotate at different rates. Magnetic regions emerge. Sunspots evolve. Fields twist and shear against each other. Over hours or days, magnetic stress can build. One useful way to picture this is to imagine a collection of elastic bands being slowly twisted. For a while, nothing dramatic happens. The structure simply stores more energy. At some point, however, the arrangement can no longer remain in the same state. In the corona, the release does not occur because an elastic band snaps. Magnetic fields change their connectivity through reconnection. Large structures can lose equilibrium. Plasma can be accelerated outward. A configuration that had been relatively stable can reorganize remarkably quickly. One important structure in many eruption models is called a magnetic flux rope. A flux rope is a bundle of magnetic field twisted around a central axis. Plasma can become trapped within and around it. Sometimes a flux rope exists before an eruption. In other models, important parts of it form during the eruption itself through reconnection below the rising structure. Either way, once the magnetic configuration becomes unstable, the flux rope can begin lifting away from the Sun. As it rises, magnetic reconnection can continue underneath it. That releases additional energy. The structure accelerates. Hot plasma brightens below. A flare may develop, and the expanding magnetic system begins becoming a CME. This process can also involve a prominence. Those are the relatively cool structures we encountered earlier, although cool still means temperatures around 10,000 degrees Celsius. Prominence material can be suspended inside magnetic fields high above the visible solar surface. When the surrounding magnetic structure erupts, the prominence can rise with it. To an observer, the event may begin as a dark or bright filament near the Sun, then expand into the corona as a much larger disturbance. This is one reason the inner corona matters so much. By the time a CME is easily visible in an outer coronagraph, some of its most important development has already occurred. The magnetic structure has begun expanding. A substantial amount of acceleration may already have happened. The eruption has interacted with nearby magnetic fields. Its shape may have changed. If scientists want to understand the cause rather than simply watch the result, they need observations closer to the solar surface, and once again, that is precisely where ordinary coronagraphs have had trouble. The bright solar disk forces conventional instruments to hide part of the inner corona. Extreme ultraviolet telescopes can observe activity close to the surface, but their field of view does not always extend far enough to follow a CME continuously outward. Then, farther from the Sun, conventional coronagraphs pick it up again. For years, solar scientists have often had to connect those two views. Here is the eruption beginning, then there is a gap, then here is the same general eruption farther out. The missing interval can contain some of the most important acceleration and restructuring. Probe 3 was designed to put an instrument into that gap, and on July 16, 2025, ASPI-ICS captured exactly the kind of sequence that shows why this matters. The event could be followed using 3 European solar instruments working across different regions around the Sun. Probe 2's SWAP telescope observed the solar disk and low corona in extreme ultraviolet light. Probe 3's Aspix coronagraph covered the inner corona. SOHO's LASCO C2 coronagraph watched the higher corona farther out. When the observations were combined, researchers could follow the coronal mass ejection from close to the solar disk, through the previously difficult inner region, and onward into the outer corona over roughly an hour and a half. That continuity is the important part. Imagine watching someone throw a ball, except your first camera shows the hand beginning to move, and your second camera does not see the ball until it is halfway across the room. You can measure the speed later. You can estimate the trajectory. You can probably reconstruct what happened, but you missed the moment when most of the acceleration occurred. Add a camera covering the space between them, and now you can watch the entire motion. The same logic applies to a CME, except the ball is an expanding magnetic structure containing an extraordinary amount of plasma. With continuous coverage, scientists can measure how the front of the eruption moves. They can watch its width increase. They can track internal features. They can see whether acceleration is smooth or occurs in stages. They can compare the eruption with the magnetic activity seen closer to the surface. Those measurements can then be tested against models of how CMEs begin. There are several competing and overlapping models. Some involve magnetic reconnection, gradually removing field that had been holding a flux rope down. Some involve an instability in a twisted magnetic structure. Some emphasize the balance between an expanding flux rope and the overlying magnetic field restraining it. In many real eruptions, several processes may be involved at different stages. This is why observations are so important. A theory can produce a convincing animation. The sun is under no obligation to follow it. Researchers need actual positions, speeds, accelerations, temperatures, densities, and magnetic constraints. The more of the eruption they can observe directly, the less they have to infer from what happened before and after. The earlier stages are also important because CME acceleration can be extremely rapid. Some eruptions gain much of their final speed within only a few solar radii of the surface. That places the main acceleration squarely inside the region, where Proba 3 is designed to observe. If a CME reaches the outer field of a traditional coronagraph already moving at 1,000 km per second, measuring it there tells you the result. Watching it go from 100 to 500 to 1,000 km per second tells you about the force. And force is what the models have to explain. Magnetic pressure can push outward. Magnetic tension can either restrain or accelerate structures depending on the geometry. Plasma pressure contributes. Gravity pulls inward. The surrounding solar wind affects the expanding CME. Reconnection can continue adding magnetic flux and energy to the eruption as it rises. All of these effects can change with height. A CME, therefore, does not behave like a cannonball that receives one push and then coasts through empty space. It evolves. Its magnetic field expands, its density falls, its internal structure changes. It can accelerate or decelerate. A very fast CME may plow into slower solar wind ahead of it and form a shock. A slower CME can be pushed or reshaped by surrounding streams. Two CMEs launched at different times can even interact with each other before reaching Earth. The useful prediction is not simply something left the sun. We would like to know where it is going, how fast it is moving, how fast it will be moving tomorrow, how wide it is, what its magnetic field looks like, and whether Earth is actually in its path. That last question sounds straightforward until you remember that coronagraph images flatten three-dimensional structures into 2 dimensions. A CME coming directly toward a coronagraph can appear as a halo expanding around the sun. One moving sideways may show a much clearer profile. Determining the true direction and shape can require observations from multiple locations and sophisticated modelling. Proba 3 does not solve that geometric problem alone. Its strength is giving scientists a better look at the eruption before it reaches the regions where other coronagraphs already perform well. That earlier information can improve the starting conditions given to models, and starting conditions matter. If you're trying to predict where a hurricane will be in 2 days, your model becomes much less useful if you begin with the wrong location and wind speed. Space weather models have the same general problem. Small errors close to the sun can grow as a CME travels tens of millions of kilometers. Knowing the early acceleration more accurately gives the model a better chance farther out. There is one part of CME forecasting that remains particularly difficult: the magnetic orientation. Earth itself has a magnetic field. When a CME arrives, the interaction between the CME's magnetic field and Earth's magnetosphere strongly influences how severe the resulting geomagnetic storm becomes. If the magnetic field carried by the CME has a strong southward component when it reaches Earth, it can connect efficiently with Earth's northward-facing field on the day side. That allows more solar wind energy to enter the magnetosphere. The result can be stronger geomagnetic activity. A CME can therefore be fast and aim toward Earth without automatically producing the strongest possible storm. Its internal magnetism matters, unfortunately remotely determining that magnetic orientation while the CME is still near the Sun is extremely challenging. Visible light coronagraphs mainly measure scattered sunlight from electrons. They show density structure beautifully. They do not simply provide a complete three-dimensional map of the CME's magnetic field. Researchers therefore combine coronal observations with measurements of the source region, magnetic models, radio observations, other spacecraft, and eventually direct measurements made as the CME approaches Earth. Proba 3 contributes another piece, not the entire answer. That distinction is important because new missions are often introduced with the tempting phrase, "This could transform space weather forecasting." Sometimes that is true. It rarely means tomorrow's forecast suddenly becomes perfect. Better observations improve the physics. Better physics improves the models. Better models can eventually improve forecasts. That chain takes careful work. Proba 3's first scientific value is that it can reveal motion close to the Sun that previous space coronagraphs could not routinely follow at the same detail. ESA's, April 2026. Science Update described the inner corona as the region where space weather is born and highlighted CME formation as one of the major open questions the expanding ASPI-ICS dataset can address. By that point, 57 artificial eclipses had already produced more than 250 hours of high-resolution coronal video. 250 hours is especially valuable for eruptions because nobody can schedule a CME. Scientists cannot send a message to the Sun asking for one at 14:30 on Tuesday when every instrument is ready. Eruptions occur when the magnetic conditions allow them. The best strategy is to observe for long enough that interesting events eventually happen inside the field of view. Natural total eclipses are terrible for this. A team can spend years preparing for a few minutes of totality and see a beautifully structured corona that happens to do absolutely nothing dramatic during the observation. That is still scientifically useful. It is less convenient if your research proposal contained the phrase, "Observe the birth of a coronal mass ejection." Proba 3 can accumulate hours, then more on another orbit. The longer it watches, the greater the chance that a prominence erupts, a streamer changes, or a CME crosses the inner corona while the artificial eclipse is active. The September 2025 observations we encountered earlier showed this advantage with prominence eruptions. During one roughly 5-hour sequence, ASPI-ICS recorded 3 separate prominence eruptions. That does not mean all 3 became large Earth-directed CMEs. It demonstrates the observing opportunity. Instead of obtaining one still view of a prominence and wondering what happened afterward, scientists can watch the structure rise, expand, fragment, and move through the surrounding corona. This time dimension is what turns morphology into dynamics. You're no longer asking only what shape is it. You can ask, how did it become that shape? For eruption science, that is a much better question. A large CME can begin from a region that looks comparatively modest. The magnetic energy is invisible. What the telescope sees is plasma responding to that magnetic energy. A loop begins rising, a prominence lifts, material drains along field lines, a cavity expands, bright fronts appear, the eruption accelerates. Some of the most important evidence is not spectacular by itself. It may be a slight upward movement several minutes before the main event. It may be a gradual expansion. It may be material starting to flow along a neighbouring structure. Long continuous observations give researchers a better chance to recognise those precursors. That does not mean Proba 3 will become a machine that announces every CME before it happens. Predicting eruptions before they begin is an even harder problem. Solar active regions can store magnetic energy without erupting. Some configurations remain stable for days, others become unstable. 2 regions can look similar in ordinary observations and behave differently. Scientists are still trying to determine which measurable changes are reliable warning signs and which are simply normal magnetic evolution. The inner corona provides additional evidence. If a structure begins slowly expanding before a CME, ASP, IICS may see part of that evolution. If surrounding streamers are deflected, that becomes measurable. If material begins moving outward before a large eruption becomes obvious farther away, the timing can be compared with flare and magnetic observations closer to the surface. The more complete the sequence, the more precisely researchers can reconstruct what happened. And reconstruction is often how prediction begins. You first learn which events consistently precede an eruption. Then you ask whether those events can be recognized early enough to be useful. Solar physicists have been following that process for decades. Proba 3 gives them one more region of the Sun to include. There is also a more immediate reason to study CME development. The eruption has to push through the ordinary solar wind we just discussed. Those two subjects are not separate. The background wind determines the environment into which the CME expands. A fast CME travelling into slow wind can generate a strong shock. A slower eruption inside a fast stream may evolve differently. Nearby coronal holes can influence its trajectory. Magnetic pressure from surrounding structures can deflect it away from the direction it initially appeared to be travelling. So understanding the normal corona improves our understanding of eruptions. And studying eruptions teaches us about the normal corona by disturbing it. It is similar to watching waves around a boat. If the water were completely still, the boat's wake would reveal something about the water. If the water already contained currents, the interaction between the wake and those currents reveals even more. A CME is an enormous disturbance moving through an already active magnetic atmosphere. Proba 3 can watch the first part of that interaction. Farther out, SOHO continues the view. Elsewhere, Solar Orbiter and Parker Solar Probe can measure related plasma and magnetic conditions. Near Earth, space weather satellites watch what finally arrives. The complete picture begins to resemble a chain of observers stretching from the solar surface to our planet. No one instrument sees everything. That is normal in modern solar science. The important development is that one of the largest gaps in the chain has become much smaller. The July 16th CME demonstrated that visually. Proba 2 saw the beginning close to the solar disk. ASPIICS followed it through the inner corona. LASCO continued tracking it farther away. For once, the eruption did not have to disappear from one instrument and mysteriously reappear in another before scientists could continue following it. That is what filling the observational gap actually means. Not merely adding another pretty green ring to a composite image, it means preserving continuity. And continuity is valuable whenever you are trying to understand change. The same principle applies to the corona's temperature, to the acceleration of the solar wind, to prominence eruptions, to coronal mass ejections. Each problem involves processes that develop across height. If observations disappear for part of that height range, the physics inside the gap has to be reconstructed. Now less of it does. And after all the attention we have given the new solar observations, it is easy to forget that Proba 3 was built to prove something even larger than a new way of studying the corona. The artificial eclipse is the scientific experiment, but the machine that makes that eclipse possible may be the beginning of an entirely different way of building spacecraft. Because Proba 3 has quietly changed the meaning of the word instrument. For most of the history of astronomy, an instrument has been one object. A telescope may contain many mirrors, lenses, detectors, motors, and electronic systems, but they are connected by a physical structure. The distance between the components is determined by metal, carbon fiber, glass, or some other material that holds everything in place. If one mirror must sit 10 meters from another mirror, engineers build something 10 meters long. If the instrument has to fit inside a rocket, that structure may need to fold. Then it has to unfold in space. And the larger the instrument becomes, the more difficult the process gets. Proba 3 took another approach. Its two main optical elements are about 150 meters apart. Nothing structural connects them. The mission replaces a physical support with measurement and control. The occulter knows where the coronagraph is. The coronagraph knows how it is oriented. Cameras narrow the relative position. Laser metrology refines it. Shadow sensors confirm the final alignment. Thrusters remove the error. Software repeats the process. The result behaves, for several hours at a time, like an instrument whose structure is made partly from empty space. That is the technology demonstration hidden inside every ASPIICS image. When ESA announced in May 2025 that Proba 3 had maintained millimeter precision formation for several hours without control from the ground, it was not simply celebrating accurate satellite navigation. The agency described the pair as effectively simulating one giant spacecraft. That was the point from the beginning. Once you can do that reliably, a number of spacecraft designs become easier to imagine. Some scientific instruments want a very long focal length. Others want a very large baseline, meaning the distance between separate observing elements. Earth observation systems may benefit from coordinated spacecraft, flying in carefully controlled geometries. Future servicing vehicles may need to approach satellites accurately without immediately docking. Rendezvous missions may need autonomous navigation around objects that are not cooperating. ESA specifically designed Proba 3 to test technologies relevant to future astronomy, Earth observation, servicing, rendezvous, and multi-spacecraft missions that would behave like virtual structures too large to build as a single satellite. That does not mean there is already a 10-kilometer telescope waiting in a warehouse, because Proba 3 worked. Demonstrating a capability is not the same as making every possible application easy. Different missions would require different accuracy, different separations, different propulsion systems, different sensors. Some might need spacecraft to remain in formation continuously, rather than only around the high point of an elliptical orbit. Others might require control across kilometers instead of 150 meters. Some astronomical interferometers would demand positional knowledge far beyond the millimeter scale demonstrated here. The lesson from Proba 3 is more basic. The principle works in orbit. Two free-flying spacecraft can repeatedly find each other, align, maintain a carefully controlled geometry for hours, separate safely, and then reconstruct the formation later. That is a much stronger demonstration than showing the mathematics in a simulator. Space has a habit of identifying assumptions that looked excellent in the simulator. Sensors see unexpected reflections. Thrusters behave slightly differently after launch. Thermal conditions shift. Software encounters edge cases. Hardware ages. Communication links drop. The real spacecraft cannot be paused while an engineer opens the code, and Proba 3 itself provided a reminder of that in 2026. In February, an anomaly aboard the coronagraph spacecraft caused ESA to lose contact with it. For about a month, the mission team had no communication with one half of the two spacecraft system. The recovery effort involved operators, engineers, and industrial partners investigating the failure and attempting to regain the spacecraft. Eventually, they received a signal again. Engineers then had to determine whether the spacecraft had survived the interruption, whether its subsystems were healthy, and whether ASPIICS could still operate. The root software problem was patched. By early June, the coronagraph spacecraft had been checked, the instrument was confirmed healthy, and Proba 3 successfully returned to formation flying. On June 4th, 2026, ASPIICS produced its first artificial eclipse image after recovery. ESA announced on June 9th that both the spacecraft and coronagraph were healthy and ready to resume routine operations. That episode is relevant for more than mission drama. Autonomous multi-spacecraft systems create new possibilities, but they also create new failure modes. If one element of a virtual telescope fails, the entire instrument may stop functioning even though the other spacecraft remains perfectly healthy. Future missions using formation flight will have to plan for that. They will need safe modes, collision avoidance, independent navigation, recovery procedures, reliable inter-satellite communication, the ability to separate when something goes wrong, the ability to rebuild the formation afterward. Proba 3 is demonstrating those operational realities alongside the precision technology itself, and this is probably the less glamorous part of creating a new spacecraft architecture. The first image gets attention. The recovery procedures make the architecture usable. There is another reason formation flying is attractive. Rockets impose a geometric limit before a mission has even begun. A payload has to fit inside a fairing. Engineers can fold enormous structures, and modern missions have become very good at it. The James Webb Space Telescope famously unfolded a segmented mirror and a large sunshield after launch. Radio telescopes can deploy large antennas. Solar arrays can extend across many meters. But unfolding has limits. At some point, the instrument you want may simply be too large, too flexible, or too complicated to build as one connected structure. If several spacecraft can instead provide the necessary geometry, the launch vehicle no longer has to contain the full instrument at its operating size. Each piece can launch compactly. They separate afterward. Then navigation creates the final dimensions. This could allow baselines or separations impossible for a conventional spacecraft. Proba 3's 150 meters is already a useful example. A rigid 150-meter coronagraph would have been an absurdly inconvenient object to launch. The two spacecraft version makes the same optical separation without constructing the beam between them. The solar eclipse, therefore, becomes a very practical demonstration of a general engineering idea. Do not build the distance, control the distance. For astronomy, that idea can be powerful because resolution often improves when an instrument becomes larger. An interferometer combines signals collected at separated locations, allowing the system to achieve angular resolution related to the spacing between its elements. On Earth, radio astronomers have used this principle for decades. Telescopes separated by kilometers can behave mathematically like parts of a much larger instrument. Very long baseline interferometry can even link radio telescopes on different continents. In space, the same broad principle could escape the physical limitations of Earth. Several free-flying observatories could potentially create enormous baselines. The difficulty would be knowing and controlling their relative positions accurately enough for the wavelength being observed. Proba 3 is not that interferometer. It demonstrates some of the formation navigation capabilities such future systems would require. Externally occulted telescopes offer another possibility. Proba 3 uses one spacecraft to block our sun so another can see the faint corona beside it. Astronomers studying planets around other stars face a related brightness problem. A star can be billions of times brighter than a nearby planet seen in reflected visible light. One proposed solution is a separate starshade spacecraft flying far in front of a space telescope. Its carefully designed shape would block starlight while allowing faint planets beside the star to remain visible. The separation for an exoplanet starshade would be vastly greater than Proba 3's 150 meters, and the optical requirements are different. But the underlying architectural idea is familiar now. Put the blocker on one spacecraft, put the telescope on another, control the geometry instead of connecting them physically. Proba 3 does not prove a future starshade mission is easy. It provides flight heritage for the broader concept that an external occulter and telescope can operate as a coordinated free-flying system. Closer to Earth, formation flying technology could support different kinds of coordinated observation. Two or more satellites could view the same region from carefully controlled angles. Radar systems could distribute transmitters and receivers across separate spacecraft. Gravity missions could measure changes in separation with extreme precision. Some of these capabilities already exist in specialized forms. The development path is incremental. One mission proves relative navigation, another improves the metrology, another increases autonomy. Eventually, techniques that once required unique experimental spacecraft become standard engineering options. That is what happened with many technologies now considered ordinary. Autonomous navigation was once unusual. Electric propulsion was experimental. Small satellites were often treated mainly as educational projects. Reusable rockets once sounded commercially unrealistic. Space engineering tends to become normal shortly after people stop being surprised that it works. Proba 3 may eventually experience the same fate. Today, 2 satellites maintaining millimeter precision across 150 meters is remarkable. A few decades from now, engineers may discuss formation flying tolerances in a design meeting with the same enthusiasm currently reserved for battery capacity. If that happens, Proba 3 will have succeeded in the way technology demonstrators are supposed to succeed, by becoming less special. Its solar science, however, will remain valuable on its own. By April 2026, the mission had completed more than 60 highly accurate formation flying orbits, with 57 used to produce artificial eclipses. Those observations had already yielded more than 250 hours of high-resolution coronal video. ESA noted that much of the dataset had not yet been fully analysed when the first solar wind results were published. That means many of the most interesting results may not have appeared yet. Scientists still have to search those sequences for more wind structures, more eruptions, more prominences, more waves, more unusual motions. They can compare observations taken under different magnetic conditions. They can test coronal models against an expanding library of real inner corona images. They can investigate whether solar wind accelerates. They can follow CMEs while their structures are still developing. They can look for clues to how energy moves through the corona. And they can do all of this with observations repeated by the same instrument instead of waiting for the moon. That last point deserves another look because it is easy to become accustomed to it. For most of human history, seeing the full solar corona required a natural total eclipse. People travelled enormous distances to stand beneath the moon's shadow. Astronomers transported telescopes across continents. Expeditions succeeded or failed depending on weather. Some eclipses helped establish major scientific ideas. Others produced beautiful records of the changing corona. But the observing window was always temporary. The moon moved on, sunlight returned, the corona disappeared. Proba 3 takes one of astronomy's rarest observing conditions and converts it into an engineering procedure. Align the spacecraft, center the shadow, begin the observation, hold the formation, collect the data, separate, return on another orbit, repeat. That does not make natural eclipses scientifically irrelevant. Ground-based eclipse observations can still achieve remarkable spatial resolution, use specialized instruments, and cover parts of the corona in ways that complement spacecraft. What has changed is dependence. For the specific problem of obtaining long, repeated observations of the inner corona from space, researchers no longer have to rely entirely on a fortunate alignment of 3 natural bodies. They can manufacture the relevant alignment themselves. There is something almost comically human about that. Nature provides a total eclipse for a few minutes. We look at it. We decide it would be useful to have longer. Then we spend years building 2 satellites, launch them into a 19-hour orbit, teach them to measure one another with cameras and lasers, and arrange for one to cast an 8-centimetre shadow onto the other from roughly 150 metres away. All because the sun was a little too bright. And after all that effort, the reward is not an obviously spectacular new object. It is a better view of something that had been surrounding the sun the whole time. That may be the most interesting part of this story. Nothing Proba 3 revealed was hidden behind a distant planet. Nothing was buried beneath the surface. The inner corona sits immediately beside the most observed object in our sky. The problem was contrast. The sun itself was preventing us from seeing the environment around it properly. Once engineers removed enough of that light, the missing structures appeared. Then the structures moved. Some moved much faster than expected. Some moved inward. Some accelerated through streamers. Prominences erupted. A coronal mass ejection crossed the gap between instruments. The quiet halo of an eclipse turned into a dynamic plasma environment, and the old questions became more precise. Why is the corona so much hotter than the surface below it? How does magnetic energy become heat? Where does the solar wind receive its acceleration? Why is the slow wind so structured and variable? How are coronal mass ejections assembled and accelerated? How early can we recognize the features that determine whether an eruption becomes important for Earth? Proba 3 will not answer all of those questions by itself. No mission does. But it has changed what can be measured while scientists try. That is often how progress actually happens. A mystery does not disappear. The available observations improve until the mystery becomes specific enough to attack. Instead of asking vaguely why the solar wind accelerates, researchers can ask why one plasma structure moves at 100 kilometers per second, while another nearby feature reaches 400. Instead of inferring what a CME did between the low and outer corona, they can watch more of that transition directly. Instead of describing the inner corona from a handful of brief eclipses, they can accumulate hundreds of hours of repeat observations. Better questions are one of the main products of better instruments. There is also a nice symmetry in the scale of everything involved. The Sun is about 1.4 million kilometers across. Its corona extends millions of kilometers farther. Earth orbits roughly 150 million kilometers away. And the new view depended on controlling two small spacecraft separated by only about 150 meters. A difference of a few millimeters between those spacecraft could affect our ability to study structures tens or hundreds of thousands of kilometers across. Solar physics has apparently decided that scale should remain inconvenient at every opportunity. But perhaps that is what makes the mission so satisfying. The solution is precise rather than enormous. One disk, one telescope, two spacecraft, a narrow shadow, and enough autonomy to keep all of it aligned. If you're still awake, you're now a little farther along than when we first looked toward the Sun and wondered what could possibly remain hidden around something so familiar. We began with glare, then diffraction, then two spacecraft pretending to be one telescope. We followed their artificial shadow into the inner corona, where temperatures climb above 1,000,000 degrees and plasma moves through a magnetic environment far less orderly than a still eclipse photograph suggests. We watched the slow solar wind turn out to be unexpectedly fast in places. We followed an eruption through the observational gap, and we ended up with an instrument whose most important component may be the empty space between its two halves. If the Sun is below your horizon now, none of this has stopped. The corona is still shifting, the solar wind is still leaving, magnetic fields are still storing and releasing energy. Perhaps somewhere on the far side of the Sun, an eruption is beginning that nobody near Earth can see yet. And when Probe 3 reaches the right part of its orbit and its two spacecraft form up again, the occulter will move into position, the coronagraph will settle into its shadow, and the bright disk will disappear from the instrument's view. For a few hours, an eclipse will exist when no moon is passing by. If you have found this slow trip around the Sun soothing, interesting, or simply useful company while the day winds down, you can leave the video a like and subscribe to Science for Sleep. It helps this quiet corner of science reach other people who might also enjoy discovering that even our nearest star can keep something hidden for a surprisingly long time. And wherever you happen to be listening from, perhaps look toward the direction of the Sun tomorrow. Not directly, of course. Your eyes have made it this far and deserve continued employment. Just remember what surrounds that familiar bright disk: 1,000,000-degree atmosphere, magnetic loops, streamers, plasma blobs racing outward, material falling back, solar wind being assembled, eruptions beginning their journey across the solar system, most of it invisible in an ordinary sky because the Sun is simply too bright for us to notice. We did not have to travel to another star to find something new. We only had to learn how to hide this one carefully enough to see what had been there all along. And somewhere high above Earth, two small spacecraft are doing exactly that. Separated by about 150 meters, holding a shadow to within millimeters, and quietly watching the Sun reveal what it was hiding.